Alrighty then. Yeah, I think we've got everything set up here. Cool. So this doesn't really need to be over here. This is started writing up a whole post on inverse kinematics and what we've learned from the last couple streams. So hopefully that'll turn into like a post on my blog and like an actual inverse kinematics video, which I'm pretty excited about. Let's see. Does this look like it's working? I think it is. Cool. I see people hearting. So we did, I guess last time we were on stream, we were really doing 2D. So let me show the 2D, which should just be, yeah, ready to build. So we've got that, the current state of 2D is like, we use X as forward. And we assume that all inverse kinematic bone chains are going to be connected by the length from each transform to each other transform, each joint to joint, right? Good morning, Keaton. How are you? So they start off like this because by default, all transforms start off X to the right, even though X is kind of like forward. I guess we could make Y forward. It's just a difference of changing the quaternion handling. I split this out into a main and a lib, and I greatly simplified all the code. So where's our quaternion handling? Our quaternion handling is basically from axis angle for a quaternion around the z-axis, and then we use the vector from point to point, from like joint to joint, to figure out where we should rotate. So if we wanted to change this to y, we could just add, negative 90 degrees or something like that. So it's configurable, but for now, this is the state of the 2D inverse kinematics, which is a bunch of bones, all the rotations for all the transforms, also all the like red, green axes are just an axis 2D gizmo in Bevy. The blue pills, I guess, capsules, whatever you want to call them, blocks, are meshes attached to each of the bones. So we can go from the end of a bone up through the chain to an arbitrary number of bones to control those as inverse kinematic bones. And overall, very, very cool, very good. And I extended that to 3D. I guess I was running in release, but so 3D also working. Also with the rotations, also with everything set up. So this is just a sphere moving in kind of a combined set of sine waves or whatever. And the bones are trying to reach to the center of the sphere. Which is working out pretty well. And then the only real change between those two was the quaternion handling. So again, this quaternion handling here, which is basically, maybe I can make this a little bit bigger. This quaternion handling for each of the bones. We do from axis angle for 2D, which calculating angles in 2D is much simpler because you go point to point, you get the vectors, you subtract them, and you go, it's a rotation, I promise. But in 3D, the quaternion goes from rotation arc in this sense. And I chose to go from a rotation arc that is like 0, 0, 1. So 0, 0, 1 on the z-axis. And that points kind of positive z in the direction that we want to go. In Bevy, technically world space negative z is forward. So if we do a negative one here instead, we can see that that actually inverts the direction that z is facing. So I haven't really decided what the right approach is there, but we have both of them open to us. It's like a very easy change, right? Hey, Xavier, how's it going? See, my rotations are working. Rotations in 3D even. So very happy about that overall. I'm going to leave it at 1 for now. I assume that when we start talking about like exporting things from Blender, we'll have to have a minor discussion about coordinate spaces and how the transform happens from Blender to Bevy, etc. See, the code is much better documented. Yes, it is. So the code for 2D and 3D is basically the same, which is really cool. Let's see. Do I have my git diff? Those are not the git diffs that these are not the git diffs that I'm looking for, nor the droids. Maybe I did GD. I did GD. I think I'm in the right directory. Let's see. Inverse kinematics, 2D. Which directory am I in? I'm in the root. So this will be no index. This will be there. This will be, oh, I guess I was in 3D when I did this. Inverse kinematics. Right, so just comparing the two files. Couldn't access. Oh, examples, because I'm not in it. I'll go into examples. That's why my autocomplete wasn't working. So this is the total diff between the two, 2D and 3D. We've got, for 3D, mouse position isn't really a thing. I just left it there so that the diff would be clean. Mouse position in 3D is just the sphere position, so it's the target, which I should rename. And in 2D, it's actually the mouse position on screen. So you can see that this is just like a swap to 3D. The current position for the bones in the bone chain is a vec3. The tolerance changes. So tolerance in 2D, a tolerance of 1 is 1 pixel, but in 3D, 1 is 1 meter. So a tenth of a meter seems to be fine for that tolerance, but I guess that could be configurable on like a per chain basis or something. That's a comment. This is a gizmo that basically just got different formatting because I removed .xy, so it's a vec3 instead of a vec2. Again, removal of xy, vec3 instead of vec2, xy, distance as a vec3 instead of a vec2, vec3 instead of a vec2. I removed the width alpha from the 3D because it's not necessary. Yeah, vec3 instead of vec2, and then the only real change is the quaternion handling. So it's the entire algorithm, as the way we wrote it for 2D, also works for 3D, given the replacement of vec2s and vec3s, and just a difference in how do we actually calculate a quaternion in those two. I assume that we could actually do a generic quaternion handling here, but I'm not sure that's actually worth it. Tolerance could be proportional to the original difference. The original difference of what? The original difference of well, here, I'll show you why tolerance is actually required. We go to tolerance in 3D, and we set this to a value that, so note that for 3D right now, everything is smooth. Everything works just fine. It is kind of like fluidly matching to that position. The gizmos maybe are a little bit out of sync, very, very slightly, but they are pointing to the right position, and everything's working to get it to the right spot, right? The tolerance, if we change this to be like a meter, wreaks havoc on the output. So here you can see the algorithm actually ends up reaching a position at which it's comfortable just stopping in a lot of cases, and just stops. And the cases in which it stops, if I remember my logs correctly, are cases in which it basically only needed one iteration or no iterations to reach a valid position for the end position. So if the tolerance is going to be higher, then there needs to be some other changes as well, I guess. But that is why the tolerance is here. I think the tolerance could be probably as low as 0.001. But I think once we hit 0.001, there's another function in our algorithm that actually only has an accuracy of 0.01, sorry. So that would be also become an issue. The original difference between the chip of the last bone and the chain to the target position. Yeah. So the other thing about the algorithm is that it uses the last position to do the next position. So I don't actually think that would have a great impact. Hello, everyone. Hello, Sorav. How are you? So overall, very happy with this. There's no constraints or anything. Might as well kind of like go over, I guess, some of the code because it's been a while since we covered it on stream. So this is the 2D inverse kinematics. I guess I can play it on the side while we do this. Because it doesn't move very much. But you can see that everything's handled appropriately, like all of the edges and stuff. So inverse kinematics 2D, this is the main.rs. This is doing the application setup. So I switched it into a main.rs and a lib.rs. We've got a background color, which is that blue in the back. We've got a gizmo group for writing the dotted gizmos. You can't see the dotted gizmos because we added meshes in currently. The dotted gizmos are the lines behind the meshes, effectively, I think. Or actually, you know what? You can see them. It's just really tough because we put X in the direction of movement, which means that well, this is a mouse-based demo, so I can't really show that. But if you can zoom in to where my mouse is, there's a little bit of the gizmo that's showing, even though there's still the arrow from the previous bone going in that direction. I'm good, enjoying this interesting video. Cool. So we had the default plugins, we had a startup system to spawn some stuff, and we add debug transforms and process inverse kinematics. So like debug transforms is not critically necessary. That's where all the arrows are coming from. Oh, there's no comma on that. I wonder if that'll matter. So this is the actual like inverse kinematics without the debug stuff. And you can kind of see the gizmos lined up in there. This is a little bit far away to look at, but so we end up with this like chain and it moves around and whatever. So startup system is responsible for spawning stuff in. Process inverse kinematics is our entire FABRIK implementation. Startup, very simple. Configure some gizmos, spawn a 2D camera. There's a couple of different, I don't know what to call them, like scenes worth of like bone chains that I used for testing. Those could all be different examples at this point. The current way that this works is we still have a bone length here. I guess I didn't remove the bone length. I was going to. I didn't yet. So the bone length here is like a defined distance. In the future, this will come from the original like joint to joint distance, I think. But for now, it's just a defined distance. Then we have a bunch of children, meshes inside of there, more joints inside of there with bone lengths, more children, more bone lengths, more children, more bone lengths. So we end up with this like hierarchy of bones, and each of the bones has their own mesh 2D children. Is there a reason you were allowing the object earlier to go through the surface, no physics? There's no physics at all. There's no avian and there's no physics. You know, there's no physics package installed in any of these demos. So if we wanted physics for whatever reason, we would have to implement it. That's why the object goes through the surface, because there's literally nothing. Ragdolls do not need IK. Cool. So we spawn in all that stuff. Here's our debug transforms. We're just querying for all global transforms, and then Gizmo's axis 2D. In 3D, this is axis 3D. We're observing the mouse based on the pointer movement event. Query for the camera, query for the resource that stores the mouse position. Or we want to rename this to target. Do some very light math to do camera transform plus pointer position, and insert that as the mouse position. So that's our target. So this is the entire main.rs, just some setup. And then we get into the actual lib.rs. Lib.rs is only 340 lines at the moment, which is cool. Because definitely while we were writing it on stream, it got a little bit longer. The mouse position here should really be target. And I think we're going to want a target like per IK chain at some point here. But I think I might take the code that we have and bring it out into a different demo and leave these two in the repo here. So mouse position is basically target. This is our Gizmo config group. We've got inverse kinematic end effector. So if we briefly go back to our initial setup, the way this is all configured is at the end of the bone chain, there's this one component called inverse kinematic end effector. And that gives us a count of the number of bones that we need to deal with going back up the chain. So in this case, it's 6, it's all of them. We could make this 3, and it shouldn't have any effect, although I haven't tested this. Right, so now we're getting only a few of them in this bone chain. Go 2 or 4 or 5 or whatever. There are some things that need to be dealt with in that case, if we do that. But yeah. Well, actually, I don't think anything needs to be dealt with because all the visualizations are correct here. So what's happening is that 0, 0 is still down here, and the bone chain radius visualization is this circle. So you can see how it got smaller to only deal with the 2 bones and whatnot. But these other bones aren't set up to look good like that. So, which library are you using for the calculations? No library. There is no library here. This is all completely new FABRIK implementation. So I never have a Chrome window open. We all know that. So give me a second to open a Chrome window. Oh, that's not what I meant to do. FABRIK. No, I didn't mean clothing. Let's see. IK. This. So we are using the FABRIK algorithm, and we've done an implementation in Bevy. Oh, GLAM is the linear algebra lib of Bevy. Yeah, so anything where we're doing vector minus vector or quaternion from axis angle, those low-level calculations are GLAM. Okay, so we've got the target, our Gizmo config, the inverse kinematic end effector. This is what we would need to put onto the end bone, and then the bone length. And the current position is interesting as well. So previously we were using a bunch of tuples. I find tuples confusing, and there's really no overhead to using a struct. So using a struct now. So this is when we talk about the vec of current positions for the algorithm later, we have a struct that has a vec2 position, the bone length, and the entity, because that's just the information we need for processing later. We've got a constant for tolerance right now, although this could theoretically be like tolerance per bone chain. This could go into the end effector config. And then we've got process inverse kinematics. This is the function. Well, it's not the function. This is the entry point to being able to do any of the FABRIK calculations. Let's just run this in the side, I guess. So we've got all of the end effectors. Remember that component that had the bone length. All of the entities that have the end effectors on it, as well as their global transform. So this algorithm is operating in global space. So we're grabbing global transforms. We grab global transforms in a number of different queries, but because we never mutate global transform, it doesn't matter. Parents is going to be, we're going to iter ancestors to go up the bone chain. So we need to be able to do that. This parents query is for that. Bone lengths is every entity that has a bone length. So if we have a bone, it will have a bone length component, except for the end tip that is not required to have one. Gizmos, dotted gizmos, these are just gizmo configs. This is our target. This is where we are going to, or where we're trying to get the end of the bone chain to actually reach. We are going to mutate transforms at the end of this whole query. So we get mutable access to those transforms. And then we get all of the global transforms so that for any entity, we can always get the global transform if we need it. So if there's no target, we skip, because if there's no target, then there's nothing to go to, right? If there's no place to go, there's no place to run the algorithm to try to get to. So we just return. This is a labeled loop that goes over all of the end effectors. So any entity with an end effector, which means in practice, this is any IK bone chain. So this is our loop over all of the IK bone chains. That gives us the end effector entity, the end effector data itself, and the global transform. And in this case, we're iterating ancestors to find the root entity, parents, iter ancestors, and affected bone count -1 is really the calculation here. So this gives us like that root bone that doesn't move. Once we have the root bone that doesn't move, we have to check to see if the total length of all bones is, we'll get to that later. We have to calculate the total length of all bones. So we go iter ancestors again. We take all of the bones that we're looking for. We filter map. Actually, this take, I think this take is correct. Yeah, that's nth. This is take. So we take a number of iterations going up to the root. We filter map them to get that bones queries, and we get the entity. And if it has a length, then we use it and we sum them all up, and that's our total length. So far, we have a loop over all the IK bodies, the root entity, and the total length of bones. You're a bit suspicious about this last bone tip. Does Bevy need this for animation? Probably not. This is a node, not really a bone. Do we need to spawn a transform for this with IK? Yeah, why are you suspicious about it? Like, the last bone doesn't make a difference, right? Like, I don't think according to the algorithm, the last bone really makes a difference. The thing that the last bone tip makes much easier is the position of the last bone tip is the position that we're trying to get into that target, right? So if we didn't have a tip, we would need to calculate the length of the bone from the last bone, and then try to move the tip of that bone. So we would need to calculate that global position instead of just having it. But fundamentally, it doesn't make a difference, right? Like, that's not really an important part of the algorithm. You're suspicious because it's a bit different than what Bevy skinning needs? What do you mean by that? I mean, like, it doesn't, like, the tip bone doesn't matter. If we don't want to have a tip bone, we don't have to have a tip bone. Like, it fundamentally doesn't matter. Right? Like, it doesn't impact anything. It doesn't make a strong difference. What it does give us is it makes it clearer about what position we're actually using to match against the target, which in this case is useful because this is effectively going into a repo where other people can learn from it. So yeah, we could get rid of that extra tip. And would it have a great impact on the algorithm? I'm not sure it would. We could theoretically calculate the position of the tip of the bone, but that just feels confusing, right? Can the crate be used currently to add inverse kinematics in a Bevy game by providing an API, or does it just provide examples and has to be copied, rewritten? Right now, it would have to be copied, rewritten. I haven't. Basically, we're at the point where I read the FABRIK information, I read the paper, read the slides, did an implementation in 2D, got it to work, cleaned it up, ported the implementation to 3D, and that's where we are right now. So we have 2D and 3D implementations, but it hasn't been packaged into a crate for anybody to use. I think from here, if we're going to package it into a crate, these examples are going to go up on GitHub and just live as these examples. And then a separate crate could get built with the implementation, ideally generalized, right? Like the 2D, 3D difference is not super important. So we could do something like Avian, which has a scaler that controls that argument. But right now, it's not a crate. Right now, it's not published. It's just these two examples. So if you wanted to use it like right now, you would have to copy paste it. That's not to say we won't publish a crate, but yeah, we just haven't yet. Okay, so we've got a target. We've got the root entity bone. We've got the total length. This circle is the like sphere of influence, if you want to call it, or like I don't know a better name for that. This is how far the bones can reach. In 3D, this is like actually a sphere, but it's really hard to see through the middle of a sphere. So it shows up as a circle. Then we bootstrap our algorithm, right? So these current positions are starting with the end effector. Sorry for this newbie QI. I guess you have a question that you're about to ask. You're more than welcome to ask newbie questions. This is a newbie-friendly stream, if anybody is concerned about that. So we start with the current positions, right? When do I make commits and how? It depends. There's a lot of stuff where if I'm not working with other people, then I don't necessarily even make commits. It's not a great practice. if I'm working with other people, my formulation of how to make commits is dependent on the culture of the people I am working with, right? Oh, the usize question is really simple. I'll answer that first. When should you use usize? Usize is used for indices. So if you're going to index into an array or a vec, you have to use a usize. So like if I have like 1, 2, 3, and I'm going to access index 2 on it, that this 2 has to be a usize. If you're doing something that needs to work in WASM and also communicate with other targets, you probably want to use like I32, U32 specific sizes. Because otherwise you can run into a situation where the server is 64-bit and the WASM target is 32-bit. So for example, in Leptos, if you have a 64-bit server function that returns a number and you try to deserialize a 64-bit number on the client as 32-bit, that can fail. So usize for indexing, but you can do like as usize when you do that, even if you're using U32s and whatnot. Or use usize if you don't care, if you truly want the target's size of a usize, right? Because a usize is either going to be mostly U64, U32, right? Or I64 or I32. But it can also be lower than that on constrained platforms. I prefer to specify things as I expect them to be. But yeah. Basically, when you need to pass it to something that needs a usize and don't want to cast, or when an unsigned integer the same size of a register is best. Yeah. So basically, if you don't know that you want a usize, I would use it just for the indexing. Yeah. So like here, when I do like .take, this affected body count, I believe I specified as like a U32. Because WASM is 32-bit, so usize will be U32 anyway. And that prevents me from having like a U64 that I can't actually use here on WASM. It's just a target difference. You've been using it for a value from 0 to 100, but as you've been using it, you've been getting the heebie-jeebies. Thanks for the answer. If you've got a 0 to 100 value, you can use a U8. A U8 will pack 256 values from 0 to 255 inclusive. So if you really only have 0 to 100, you can use a U8. That's the other thing, right? If you're never going to have a U16 or a U32 sized value, then you don't need to use a U16 or a U32 size number. Back to commits. I guess, Sorav, when you ask, do I write in general, do you mean like blog posts or do you mean like in commits and stuff? Michael says, they commit when it's working and you remember and have it working and before you do something that breaks it, which is a pretty common approach, honestly. But yeah, there's basically like 4 commits. There's kind of 2 approaches I take. One of them is if I'm working on a new experimental thing and maybe the experiment is successful and maybe runs too long, it just kind of like goes and I forget to commit. And then sometime later I realize, oh shit, I didn't commit. I need to commit. And then I commit it. And then I push it up to GitHub or whatnot. That's what happened. I just did a full rewrite of the Rust Adventure site Monday. And what I did was I rewrote about 5,000 lines of code. I didn't commit at all. And then I went, oh crap, I didn't commit after it was all working. Luckily that is committed and pushed up, but now there's a 5,000 line commit as the first commit in that repo now, which is not great. So for things that are experimental, it's basically like I either forget or I commit very often, right? As soon as things are working and there's a stopping point that I want to keep, commit then. Or if there is a state that I want to keep, I commit then. If I'm working with other people on an established application and I'm building a feature or I'm building something that has a specific plan, or if I was making a commit to Bevy and it was a larger feature, and I needed to make it easy for other people to understand, because that's how you get PRs merged, making it easier for other people to read, then organizing your commits, writing good PR descriptions, writing good commit messages, just becomes more and more important the more people are involved, and the less time those people have to do things. So realistically, if you're working with other people, you can still do any workflow you want, but when you go to share that with other people, you can do things like git rebase, right? So if you do a git rebase -I, something like git rebase -I head 4, right? Oh, I have unstage changes. Of course I do. Talking about commits. If I wanted to clean this repo up, I could do git rebase I head 4. This is before you put the PR up, just to be clear. Once you start rebasing and messing with history, you can end up breaking anybody who's pulled that branch or anything like that. But before you put the PR up, if you're trying to get something merged, right? If you're trying to get people to be able to understand it, these commits suck for that, right? Seems to work for 3D, make it easier to diff, minor touch-ups. Like the minor touch-ups, I could just squash that, right? So I would go in here and I would just like, I would write S, but you can write squash, or whatever you want. You can do edit, etc. So there's a lot you can do for like rewriting that history after you've written everything, and collapsing it and turning it into like a series of commits that make the most sense for other people to read. And that's a really good idea. So it doesn't really necessarily matter what you do like moment to moment. But if you have to communicate that work to other people, or if you have a hard time communicating it to other people in the first place, right? Then you might want to use a more structured commit approach to help you organize the work as you do it. Things that I usually put into like individual commits are like formatting changes, right? Hey, this commit is just formatting. If you take the previous commit, you apply the formatter, you get this commit. Then somebody can just check that really easily and not expect like functionality changes. So yeah, basically like the purpose of commits in a social setting is making it easier for other people to review and read. And there's many ways you can do that. And it depends on the project. I think the more these particular examples, the ones we're building for the Bevy examples repo, which is where this stuff goes, right? So this is Bevy examples. I think I have this in a PR currently. Yeah, so here's the PR, right? This PR is like a work in progress. There's a whole ton of commits that have gone into it. I don't expect anybody to review this. I don't expect anybody to read these commits ever. This is really just like we were working on stream for a number of commits. We were working on stream for a number of commits. I worked a little bit off stream for a couple of commits. And now we're back on stream again, right? Is that a challenge? I mean, if you want to, but like, I don't think it'll be useful. Ukasu's saying that because they did a review and a PR for something that we did the other week. So Ukasu is the lone exception at the moment of somebody who would read one of these in progress PRs and then make changes. And has thus successfully passed the bar already for somebody who would read it. But I don't think you read the commits, right? You just read the end result, realistically. Because the commits aren't really that useful there. So yeah, and then like the other thing is that all of these examples typically come with a README where I write a bunch of stuff. In this case, that stuff is over here. Let's see if I can pull this up real quick. Just watch. I guess I didn't have to pull up the website. I don't have to do that anymore. I forgot. 3007, I think, is the right. So this is my personal site locally. I have a temporary post here. This is like the inverse kinematics post, right? So this is a description of everything that's in all of this source code, and thus serves as the record for somebody who would want to understand everything that is in this source code. So when we're talking about commits for things like this, it's kind of more like this is the documentation rather than the commit messages, because nobody's really reviewing those commit messages. The other thing that's really fun is I hate that this can't open. There we go. The other thing that's really fun is I've started writing in PDF form. So the post that I have right there compiles immediately to PDF because we're using Typist, right? So everything that I'm writing there can go into this PDF, and then that PDF can also go somewhere and people can read it, which I'm super hyped about. I'm so excited about Typist. Okay, commits and usizes, and Xavier had a question about the 0 to 100 and whether that was 0 to 100% if it was an F32 or not. Synapse and Salat. Ideally, a commit should be the smallest working step that is independent. In practice, it's hard to judge until a feature is complete. Use a feature branch and interactive rebase at the end. Yeah, that's what I was just explaining earlier. I think if you have if you're working in a group and you have like tickets and you're in a corporate environment and whatnot, first of all, they might not even care about the quality of the commit messages. Like it might not matter. But when it does matter and you have solid plans and like know what you're going to do, you can do that all in a line. But even then I will make a couple of smaller commits that need to get squashed in that chain, and I will squash them interactively rebase later, turn those into different things and clean it all up so that people can actually, read, understand, and merge the code that I've written. Tangent. The image animation of the paper has two IK chains that affect the same bones branch. The Gauss Seidel solver can handle that, but we do not handle that case yet. Maybe it's not useful. Which Typist package do you use for drawing? I was struggling to draw UI elements of an existing web page recently. I have not landed on anything yet. What I've considered doing recently, which I think I might have this. No, I don't want to put this on stream, but I have an iPad and I have a pencil. So I think that my approach moving forward is to actually gonna do those in Procreate and export the images. But there are packages, you are right. Typist Universe. I think Sets is one. Draw figures. I haven't worked with this at all, but maybe there's some layouts here that would work. I also don't know if this compiles to HTML. I don't know. September 8th, 2025 might. It might have like experimental support. I don't know if these get turned into images or SVGs. The problem I had, so I know how to use Illustrator and I know how to use like SVG drawing tools, and like I've been using Adobe products for 20 plus years now, and The problem I had with using, what was the SVG diagram editor, draw.io. I tried draw.io for this. And I did this, and I found it incredibly hard to use this like as an SVG. This ends up having like foreign objects in it and stuff. So is not actually compatible with throwing this into Typist, even though it is like so simple, right? Which is really strange because I would have expected this to be the thing that I could have used. But I guess it wasn't. So I need to figure it out, basically, Sarov. I don't have an answer for that yet. I want to have an answer for it. I also need to do some more complicated things that might require manually drawing things out, but yeah. Is this new? What is this? This being draw.io or draw.io? Yeah, there's a bunch of plotting and stuff, which is cool. But yeah, I don't have a solution for this yet. I'm figuring it out. Is this new? IK? Yeah. Yeah. We were going through the algorithm just before we got into some other questions, but we've got 3D IK working over here on the right with all the rotations and everything. Oh, inverse kinematics isn't new. It's a very old concept. Yeah. The concept of inverse kinematics is old. FABRIK, I think, is even pretty old. The algorithm we're using. Relatively new, but pretty old. Yeah, my implementation of it is from like last week, over the last week. So it's new in that sense, but it's not new. Also, hello, user. It's new to me in that I know what it's supposed to do, and that's about it. Yeah, so let's get back into this algorithm. The paper is from 2011. Yeah, so like new in research terms, but not new in like cutting edge terms or industry terms. You tried Inkscape as well, but that would require tutorials, I guess. I think everything will at some point. Visualizations and SVG documentation like that is non-trivial. Especially if you get into any customization or anything. So I don't know. When I find an answer, I will do that. You get IK from some game engines like Godot, but with Bevy, it looks like we, quote, get to do it ourselves. So let's see what Chris comes up with. Yeah, I mean, like, there's a couple of IK packages. I just didn't use them. All right, Bevy mod, inverse kinematics, Bevy FABRIK. So like the namespace is taken, you know? This is from yesterday. Here's some IK stuff. I don't know what they're using in here. I haven't actually looked at the implementation. Let's see, Bevy, lib, solver. We don't have any constraints yet, so from rotation arc, they do cross and everything. This is clearly a FABRIK implementation. So yeah, I don't know. There's like other, there's implementations. You mean IK doesn't exist in Bevy 0.16? It is not a built-in thing. Yeah. Yeah, exactly what Chris is saying. There's some plugins or third-party support, but there's no native support right now. We do have some constraints. IK is a constraint to put the tip to the target position. Bone lengths are constraints. Fair. I'm just not like, I guess I should frame that as extra constraints. We don't have like rotation constraints. And we don't have like joint angle constraints and stuff like that. But yeah, generally speaking, we have constraints, but we don't have like constraint implementations. But Chris is you. Chris is we. We are Chris today. I'm gonna get a square spaceship in the future. We can all fly around in it. Okay, so process inverse kinematics. If we have a target, we continue. Otherwise, we iterate over all the IK bodies, which are the ones with the end effector component on them. We find the root entity from those end effector. It's really important that we go from the bottom chain to the root here, because if we go from root to tip, then we run into issues where the root can have multiple children, one of which can be a mesh, not a bone. So if we go from root to tip, then we would either not be able to child or parent, I guess, depending on your viewpoint, meshes to the bones. So that's why we go from tip to root. We find the root entity. We get the total length of all the bones. Draw that circle that you see on the right, which is how far our bones can go out at the maximum distance. And then we set up current positions. So the algorithm operates on global positions. And here we set up all of our current position structs, which remember is a position, a bone length, and the entity. The position, in this case, we're looking at the 2D algorithm, even though 2D and 3D are the same. We set the translation XY. So this is the global position of the end effector entity. Unfortunately, there is no iter ancestors with self kind of thing. So we do actually have to have this little like standard iter once on front and then chain it into another iterator. But I'm hoping that I can find the time to iter ancestors with self and upstream that at some point. So we take all the bones as usual, and then we map over those to get all the current positions, which is all the global positions. So this current positions array ends up being, or vec, sorry, ends up being all of the global positions, all of the bone lengths, and all of the entities for all the bones. And then we put the root at the beginning because I just find that mentally satisfying, right? We reverse this list because when I think of a vec, I think of the root being at the beginning. We don't need to do this. It's just something that makes sense in my head. We get the root translation, so like the position of the root element. We need that for our FABRIK implementation because the FABRIK implementation basically pulls the chain one way, which pulls the root off, and then we have to pull the chain the other way and put the root back on. So we need to have the like the root position just always around. We have to know what that is. Then we get into like our checks for like, can we run FABRIK here? Can we even like get to our end position? Like this circle here is the visualization of that. If the total length exceeds our ability to reach the target, then we can't do anything. And the target position is out of reach. And we should align all the bones in a straight line towards the target, just to kind of like reach them at the target. To do that, we get the target direction by doing vector subtraction, right? So from our 2 minus from normalized gives us basically a dir3. So this is a normalized vec3, which is a dir3 in Bevy terms, even though it's still going to be a vec here. It's just normalized. So once we have that vector, we take the current positions. This is again moving everything in the same direction towards that target element. We use scan, which is a super interesting iterator. Scan lets you keep some state and produce a new iterator. So if what we want to do here is take all of our positions and then kind of like chain them together going forward, then we can use scan to originally keep the first parent and produce the next position using the parent's position and the target direction and the bone length. So we've got, say, like the root, and the root has a bone length and it goes in a direction, and this is the next point. And then this one has a bone length and a direction, and this is the next point. So we just keep producing those, and we collect the new produced elements into a new current positions, and then this set transforms function deals with what we'll talk about later, putting everything in the right place and rotating things. Great point. Don't you feel the urge to make it as efficient as possible? When do you decide something like reversing the list is more important than merely running after performance? When I benchmark. My final answer is, if I benchmark it as a problem, then optimizing is an option, right? Obviously the biggest answer to performance is don't do it. If you don't do it, it doesn't have a performance cost. But like in this implementation, I'm not really having any issues right now. We're running in development. We're not running in release mode. I was actually, you know what I can do right here? I can do something really ridiculous, because I was doing this off stream before. Iterations is in lib. Iterations. We haven't gotten to this point in the algorithm yet, so just give me a sec. So the max number of iterations that we can let the FABRIK solver do is 10 right now. But I can jack this up to 10,000. And I'll put a log here at the end to just info iterations. And we'll cargo run inverse kinematics FABRIK 3. And you can see that this is having 0 issues with 10,000 iterations per frame on like an 8-bone chain or something like that, 6-bone chain, whatever this is. So this is literally every update. So it's minimum 60 FPS, 10,000 iterations per frame. It's kind of fine. Like, obviously, that's not like a full benchmark. Like, if I was going to do real performance work, I would write an actual benchmark and then run, you know, criterion or something like that. But we are not having any issues, right? And because we're not having any issues, I feel no desire to optimize this. Like Xavier is saying, if you try to optimize before you profile, you don't know if you're making things better or not. So if you're going to change something for performance reasons, you have to write a benchmark, run the benchmark, view the profile, make the change, see if it impacted the profile, see if it impacted any other profiles that you might have for other use cases, and then commit to the change. Cool. So we've got all the positions. We did the reverse. Also, the reverse is not costly, right? Like, reverse is an in-place reverse. Cool. So if we can reach it, or if we can't reach it, sorry, then we do that put everything in one line algorithm. Set transforms we can talk about later. Set transforms is responsible, because FABRIK only gives you positions. What we end up with is this vec of current positions at the end of the algorithm. And we have to take those positions and translate them into a transform hierarchy with the proper rotations to point to the next point and things like that. So that's what set transforms does, but we'll talk about that later. And then we continue to the next IK body. So this isn't even parallelized, just to be clear. Like, this is just running. It's running, it's sequential, it does one and then it does the next one. Profiling without optimization. Yeah, fair. Okay, so if we should do the algorithm, right, we have a couple of things that we need to set up first. The main one being diff. And diff is how far our target bone is from where we want it to be. So in this case, the sphere in the 3D model is the target. So like the center of the sphere. So how far is the very end effector from that target? That's the diff. And that's where our tolerance comes in. So while the diff is greater than our tolerance, we run the FABRIK algorithm. Or if we break, if we like hit the max number of iterations, then we also stop. The time in which we would need to stop for the iterations like this is mostly if you have an unreachable position. For example, you have a really long bone and then a really short bone, but your mouse position is like towards the origin. Those two bones will never be able to reach that mouse, but it doesn't know that because it's within distance. It just can never get there. So you can hit this max in that situation. That said, this is our loop. This is our full algorithm loop. What we do is the forward pass, then we do the backward pass, then we update the diff, and if we're close enough, then we stop. If we're not close enough, we do another forward pass, we do another backward pass, we update the diff again. And then when we're done, we draw some gizmos and we set transforms. So this is the whole algorithm, really, right? Once you have all the setup done, once you have all the positions, so like given all the bone positions and the lengths and a target to go to, we run the forward pass, we run the backward pass, we update the diff. We do that a number of times, and it gets to where it needs to be. So the forward pass and the backward pass are extremely similar, and they're fairly trivial comparatively. The forward pass takes in the current positions. I've taken this in as a mutable slice. Just for preference reasons, this is how I like to take arguments when I'm taking things like vex. I take the dereft version of those vex. And then the target position. Most of this code is going to be the same. So it's going to be take that target position. Diff over original is greater than tolerance. Yeah, we could do that. Diff over original diff? Why would you need diff over original? Oh. Diff over original diff. Why would you need that though? The original diff immediately doesn't matter after the first iteration. Unless what you're saying is you're trying to keep the distance from the original, in which case just choose a different target. Whenever you know there are additional steps anywhere, you jump to minimize those. Yeah, I don't. I think I've spent a lot of time doing product development rather than micro optimization. So my preference is to get the thing working and then optimize it if it needs to be, because otherwise you end up with things like building a voxel engine or a falling sand engine or a game engine, and just like there's infinite amounts to optimize, right? There's infinite problems to optimize. You can always try to optimize another thing. It's not always useful to do that. And if you're trying to say ship a game, then doing a lot of those optimizations doesn't actually have an impact on you shipping the game. So like, it depends on what your goal is. If your goal is to build the fastest IK solver, then, you know, do some PhD level research. In which case you get to optimize the hell out of everything. My game's not done, but this pathfinding algorithm is terrific. Oh. My issue with that is always, I do so much educational content and I span so many different examples that I spend a lot of time building a lot of different things. And then finding the time to put it all together into a single game can be tough. That's originally why I started streaming Bevy on Saturdays. But if I only do Saturdays and I only do a couple hours on Saturday, then I basically get like a game jam amount of time every 3 months, which is not that much. So I don't know. Maybe I'll prioritize that a little bit more in the future. So now you do it on Odin's Day? Is that Wednesday? I don't know which day Odin's Day is. Wednesday, Odin's Day? Okay, cool. Okay, so current positions, we take in this mutable slice of current positions and the target we want to get to. We grab, this is like the forward pass. So forward pass is from the end effector to the root. That's just the way the paper describes it. That's what they call a forward pass. I changed my wording to line up with the paper, even though to me, this feels like a backward pass, right? From the end to the root feels backward to me. But they call it forward. So this is a forward pass from the end effector to the root. Just Norse methodology humor. No, it's funny. I appreciate it. So we get the end effector position, right? And we set that to the target. This is our first iteration of the forward pass. We take wherever our end effector is and we just set it to the target immediately. Then we take all of the other iterators, or all the other bones in an iterator. We do this in reverse because current positions is again root to edge, root to end effector. So we reverse that. We make it peakable. So then we end up with the ability to do a while loop here. And while loop is interesting because we can do the last item and the next to last item, and the next to last item can be a mutable peak, which is really interesting. This is a way to like kind of get around the fact that lending iterators are a bit of a pain. Like we can't do Windows mute here, just because reasons that I'm not going to get into. There is a crate if you wanted to do it. Windows mute in the lending iterator crate. This has been around for quite a while. I've used it in projects before. It works. But yeah. So we end up with doing a while loop. So while we still have items for it.next and it peak mute, that gives us the previous vertex and the next vertex, or the current vertex, I guess. We get the vector between the two vertices, which again is going to be like our direction. We normalize that. So this is the direction from one vertex to another. We take that previous vector's position and we subtract the bone length times that normalized vector, which gives us a vector in the distance in the direction that we need it to be. And that's where our current position goes. And we just do that for everything. So for every vertex, find the vector between them, get the direction, use the bone length, set the position there. Find the vector between them, use the bone length, set the position there. Monday equals Moon's Day. Tuesday is Tuesday. I don't know who 2 is. I think that's one of the ones that I haven't heard. I know Odin, Thor, and Freya. And Saturn, obviously. But I don't think I've heard of 2. Another way to not require the user to set the tolerance would be having no tolerance at all and always doing the max iterations. Yeah, that would be fine too. It's a pretty low number. I think that can be configurable, so we'll leave it configurable. But really not that important right now. So that's the forward pass. Take the end effector, move it to the position, and then kind of yank the whole chain forward using some lines. So that brings us to the backward pass. So we've just mutated all of these current positions, right? The next pass is the backward pass. But we do the same thing. We get the root translation. We set the root's position to the actual like root position that it should be, because the root's not supposed to move, remember. And then we do basically the same thing. The big difference here is that the previous and current change a little bit. So in the forward pass, this is previous minus the direction times the bone length. which is the current bone length. And when we're moving in the other direction, it's the previous position and the previous bone length, because we're going off of the root, which has the bone length on it. Whereas in the other direction, we're going to a joint that has a bone facing us. But other than that, they're very much the same thing. This code here might be generalizable in that sense, but I'm not too worried about it. So that brings us to FABRIK. This is FABRIK. FABRIK is forward pass, backward pass. Update the diff by taking the end effector and checking to see if it is close enough to that distance target, right? That's it. That's FABRIK. That's the whole thing. Once you do all the setup, the actual algorithm is like just iterate, iterate. So that leaves us with set transforms. Set transforms is interesting. It takes all of the positions, and in this case, it takes the query for all of the mutable transform references. So if we look at this function, it takes all of the positions that we've calculated, as well as a mutable reference to the query of mutable transforms. So what we're doing here is taking all the positions and trying to translate them into a transform hierarchy. If we had all global positions, for the most part, this wouldn't need to happen. We could actually not use this code. But because it's a transform hierarchy, we assume that a bone chain is a transform hierarchy, and thus we have to do this because transforms are offset from their parents, right? So we start off by saying the parent global transform is not set yet, right? So we're going to end up with the root here fairly quickly. We're going to set the root here. We do current positions iter peekable like we did before. This allows us to do an iteration over each item, but also peek for the next one to see if there is one that's there. So we get some next, or some current, sorry, and potentially the next one. We build a transform for the current node. So this is a global transform, right? This is the global X position, the global Y position, and this is 2D, so that's 0. Actually, hang on a sec. That made me think of something. I didn't leave that in there, did I? I did leave that in there. I left that in there. Okay. I found a bug. There we go. That actually looks better. I wasn't setting Z. Because I hadn't rotated the camera yet, I didn't notice. Okay, so things are better. We fixed a bug in our 3D implementation. So we build a transform that is a global position. So in this case, we have X, Y, and Z in this case is 0. This is the current vertex that we're on, right? The current, no, vertex is the wrong thing. The current joint that we're on, which has a bone length potentially. So with that rotation, we do quat from axis angle. We do a rotation around Z. The rotation around Z uses X forward. So we just get the vector between the two positions and we can just call 2 angle and we're done. If there is no next node, then we are at the last node and we are just going to use the same rotation as the parent. So we just use the parent. So at this point, we have the current node in global transform form. If there isn't a parent, right? If the parent hasn't been set yet, use the current node as the parent. That's it. We just grab the transform from that query. We set the rotation. We set the current node so that we can use this parent global transform later. So then we're iterating through. Now we're not the parent. And we end up with needing to compute the affine for the parent and the current node to get the scale, rotation, and translation, which we can then shove directly into a transform. So this is like the most complicated bit of logic that I think Bevy is doing for us, or Glam actually is doing for us. Glam and Bevy together. We're getting these transforms. We are inverting the parent transform, multiplying it by the child to get the position that the child should be relative to that parent. And then we are using that to set the relative transform actual of that entity. And then we set the parent again and we iterate again. So overall, pretty happy with this in general. I think that'll all go into a blog post. The only things that exist here that I potentially don't want are these bone lengths. I think the bone lengths are not necessarily useful. I don't know. I'm 50-50. I feel like we can set them implicitly. We don't have any concept of broken chains here or anything. So not having the bone length set would be fine as well. And then we could just do the distance from one to another at the beginning and store those. So realistically, this is just a matter of, is the user have to set that manually as a component, or do we infer it from the distance between two joints? And then for us right now, it doesn't really matter. So we're just going to leave it. If I do make the change, I'll probably make the change in both places. So we do have a bone length here, and I do think that we need to infer it for 3D. Technically speaking, we probably don't. We could just set bone lengths, but I think we should get rid of it. How do you find the time to not only do live streams, but also blog posts? Because the way I make my money is either through client work or through people subscribing to Rust Adventure. If you have a corporate education budget and you appreciate the work that I do, subscribe to Rust Adventure. I am currently actually working on a complete redo of the site, putting typist for all the content, and uploading some new Bevy workshops and Rust language stuff. That's where the quick start to Rust PDF is going to go, along with a video and other things. That's where I get my time from. You would do that. Infer the bone length for the bind pose set by the user. Otherwise, it is a bit of an invariant and something duplicated that the user needs to set. Yeah, I think it depends. I think from the perspective of a user, I could see arguments for both. I think the GLTF use case, the inference is better. But if you're doing something like Rain World, right? You're doing something like building Rain World enemies. This is all art of Rain World. I want actual Rain World graphics. Open image in new tab. We're gonna have to zoom in on this, aren't we? So I think the Rain World enemies don't necessarily need the same kind of thing. And it might be nicer to define them in different ways or adjust them on the fly. The only way you can adjust them on the fly is if that is a component that you can set. We could also set it up to be like, if it has the component, then it's overriding. But yeah, anyway. You can imagine some kind of character with pneumatic arms, where the bone length would be arranged. Some IK algorithm would alter the bone length within the range as well as the angles. Yeah. Yes, and we could do that for an out of reach position, but it is not changing the bone length, but changing the bone scale with the same length before scaling. Maybe. I don't know that scaling makes sense there. Right? Because why would you scale? Why would you have, let's say, a pneumatic arm, right? That is two pieces with one bone. I guess like to reduce the amount of bones, sure, but like I can definitely think of that being two bones and then having a constraint. But we don't have constraints yet, so I'm not concerned about that overall. The use case that I want to get to is definitely the GLTF use case. Um, this is IK with the angles being the degree of freedom. There can be other degrees of freedom for different kinds of motion. Yeah. Yeah. So the other thing is that if we wanted to do restrictions, I believe constraint implementation can go in one of two places. So it can go here, or it can go here. I think putting the constraints between the passes makes a lot of sense, right? I think that if we have extra constraints, putting them here makes the most sense, because you do the forward pass and you basically pull the whole chain off the root for the forward pass, right? And you put the target onto, or you put the end effector onto the target, pull the whole chain forward towards the end effector, and then the next pass is doing the same thing, but replacing the root position. So if you wanted to pull the whole chain and you wanted to have a constraint on the angles, doing the constraints after the forward pass, but before the backward pass corrects for the root, I think is the right place to do it. You wonder how one could implement FABRIK with angle constraints. Chris Traley had a good video that helped you implement FABRIK. Cool. I don't think I've seen that video. Maybe I'll look at it later now that I've FABRIK video. Cool. I haven't seen that video, I don't think. There's also FABRIK. So here's FABRIK, right? This is what we implemented. And then there's another paper called Extending FABRIK with Model Constraints. So we haven't looked at this at all. And I was thinking about trying to do like a spider before doing constraints. Yeah, it's just these two. So if this ever loads. Sick. I guess that paper is not going to load. I guess we don't get to read the extending model stuff with model constraints. Maybe they have the PDF. Get access to the full version of the article for $49. Yikes. So the secret of papers is even if they are in journals, if you can contact the author or get it from the author, they will just give it to you. The thing that I've seen from most all researchers, right, all people who are publishing papers like this, if you are interested in their work and you care about their work, they are super excited to like talk to you about their work. They've spent a lot of time on this, and they care about it for some reason, right? So if you are like, hey, I would love to read this paper, they will just send it to you, even if it's not available anywhere else on the internet. In this case, DOI is just like the journal, but theoretically it's supposed to be available at this link as well. I think this link is just slow for some reason, not really sure why. I think I have this in Zotero already, actually, but yeah. So tired of paid papers, the authors barely make money too. Yeah, I'm not going to get into the whole journal situation. I don't think I have enough experience with the publishing situation in academia to really say anything worthwhile, but journals definitely seem predatory in general. So FABRIK is a recent iterative inverse kinematic solver that became very popular because of its simplicity, conversion speed, and control performance, especially in models with multiple end effectors. We also haven't done multiple end effectors. I don't think we need multiple end effectors at the moment. Because I can't think of a use case for it. But it could be another thing, another fun thing to do. Anthropomorphic and robotic joint models. They have a human model that is the last implementation here, and kind of combines a lot of the joint models that they're talking about. So let's see if we can scan this quickly and figure out where they're doing. Chris, what did you study to build a career in tech? What did I study to build a career in tech? It's been decades for me, is one thing that I'll say. I got started on my own. I did Flash and ActionScript a long time ago. I did JavaScript. I got paid to write a whole bunch of other languages as well. Haskell, Go, Clojure. I did some Erlang stuff for a little while. All of those experiences were useful, but I can't say go learn 7 languages. That's not useful. I can only since you're asking me what I did, that's basically what I did. I went and I learned a whole bunch of stuff. I did a whole bunch of things. And now it's, decades later. And I have quite a bit of experience in a couple of different things. And the more I learn, the more tends to overlap. But the difference between picking things for a career and picking things because you're interested in them, or picking things because they are what you want to get done, are all different things, right? Like if you want to work at a specific company and they use Java, you have to learn Java, right? Like that's the way that works. But if you want to work with specific things, that limits the companies that you could work for, etc. So if you're talking about careers, it's a different answer. Like if you want an end effector to reach point X, but you don't care which of 3 end effectors reach it, multiple end effectors is mentioned in the paper. I think they have that's the same one that didn't load before, this one. I think this is this is actually a visualization here of multiple end effectors. So there is some root that is stuck to something, and 2 end effectors that are following different targets. Nope, that's the paper. There we go. I don't know why the papers aren't loading, but this is multiple end effectors. Basically, IK chains that have multiple pieces that can track multiple targets. So wacky flailing arm inflatable tube man is about the only use case that I can think of. Or like rope for a blimp, maybe, or I don't know. These things feel very like ropey to me, very like dangling. I don't know. Yeah, there's that shared part. So it can have multiple of these too, like multiple shared parts, multiple branches that branch off of them, etc. We don't have this implemented currently, but I don't think it's that different. I would have brought up the paper, but the papers aren't loading. It's like if you're playing piano and you want to play a wide chord. Yeah, got it. Okay, where's our... So they classify the shoulder model, the spine model, the hand model, and the strength model. Convergence proof, reachable and non-reachable targets. Very important to check whether the target is in reach or not. Simple when there's no rotational or orientational restrictions. Yep, this is total distance. Otherwise, direct construction of a line, which is what we're doing, while keeping the inner joint distance constant. This can be performed by applying only the backward step of the algorithm. Really? Instead of using the joint positions as the intermediate targets. Really? Let's hang on. I want to test that. So we've got, because I wrote a custom version of this. So we've got, I guess let's go to the 3D because we've been playing with the 3D. Do we do 3D? Let's do 2D. Let's start with 2D. So we've got this bailout condition here, right? Mouse is out of reach, yada, yada. We already have all the current positions. So what they're saying is that we can do a backward pass here with the current positions and the root translation. Do we have the root translation here? Yes, we do. This can be performed by performing only the backwards step of the algorithm, starting from the root joint, and instead of using the joint positions as the intermediate targets, using the target position. Okay. So it's not, okay. So it's not just run the backward pass, it's run the backward pass with some small modifications. That is significantly less exciting. There might be an inversion between backward forward semantics again, you think? No, I don't think so. They say only the backward step starting from the root joint. That is the backward step. Forward is from end to root, and backward is from root to end. So backward is starting from the root. In this case, you need to do root to tip. Yep, root to tip, which is the backward pass. It would need to be backward pass. It would also need to be backward pass with a position override, which I'm not terribly sure is super useful because, like, here's backward pass, right? So we could have some theoretical, like, target override, but then that makes this, like, kind of complicated in a way that it doesn't need to be, right? And then the vector that we calculate is the vector to the mouse target. Which is kind of what we're already doing. Right? Where is that code? Like, we already get that direction and then run the scan. So I think I'm just going to leave this. That is a cool thing to know, though. Maybe I'll note that down. From extending FABRIK with model constraints. Okay. What is the first thing you do when you become doubtful when explaining something to others? I mean, how do you deal with that situation? You mean if I don't know something and I realize only while I'm explaining it that I'm doubtful? If I know ahead of time, I qualify it. I either will say I don't know, or I will qualify it with something like my understanding is, or X gives me reason to see this. If I start explaining something that I think I know and then I realize I don't know it, I will just literally stop and be like, wait, I don't think I know this. or like I might not phrase it like that, but I will I will basically, like, if I've started explaining something that I thought I knew, you'll start seeing me go, oh, wait, hang on. I don't think that's true. Or something like that in the middle of the sentence. And then I will either figure it out or I will need to go look it up or test something. Sometimes you can figure it out in your head on the fly and just be like, oh, I was that misunderstanding. This is it for sure. I try not to do that for people who are just learning things. I try to know things before I explain them because that can be very distracting for people. But if I like start explaining something that I think I know and then realize that I don't really know it and that I need to go confirm, my normal process when I'm answering somebody's question offline is to actually confirm things before I say them. Right. So even things that I know, I am in the habit of, like, I don't know, if I was like, oh yeah, I could definitely reflect resources, right? I would go into a Bevy project. I might do like reflect resource and then like try to write a little bit of code to like make it happen, right? And if I can write that little bit of code, then I have confirmed what I thought was true. even though that may not be a thing that I do very often, right? Like I don't really reflect resources all that often. I reflect components a lot. And I know that because of my component knowledge, because I know how reflecting components works, and because I know the reflection infrastructure, that you should be able to reflect resources. But I will go back and confirm that that is true before giving the explanation. Do you explain the misunderstanding to the person or only explain the topic? You feel you confuse others by mixing up both. It's very easy to confuse people. I think if I'm dealing with somebody who is newer to the topic material or has already been having a hard time, right? If they've tried a bunch of things, they're getting frustrated, they are looking for help, trying to ask a question. It's really important in those cases to only come with the answer, right? So in those cases, I don't start answering until I know that what I'm saying is correct, right? And if I don't know, then I don't know, right? In other cases where people may be a little bit more confident, I can cover like the misunderstanding that I had because they have the capacity to like go through that with me. But yeah, if somebody's like super frustrated or has something else going on, it's really important actually to not mix that up. Okay. In addition, there are cases where the kinematic chain cannot bend enough to reach the target, even if the latter is within the reachable bounds. Such a case occurs. Oh, is this the case that I identified earlier? Such a case occurs when the kinematic chain consists of a link with size d that is larger than the sum of all the remaining links. That is the case of the large bone followed by the small bone. Mouse position should become target. Yes, we do need to do that. Make it a component set on the last bone of the chain or a member of the IK component. Yeah, currently you only have a single IK target. Yes, absolutely. All of that is true. Such a case occurs when the kinematic chain, I'm trying to figure out if we can early bail in this case, if that's what they're describing here. Such a case occurs when the chain consists of a link with the total size that is larger than the sum of all remaining links. What is a link? A link is a bone, right? So if you have a bone that is larger than the sum of all remaining links, and the target is located in a distance of less than half of that, is that how to read that? The distance of less than 2d max minus the sum. Technically not less than half, but less than the gap of the bone length. So we theoretically can add this calculation in. And theoretically also only run it on the second iteration. I want to be able to like note this. Do I have Zotero open? Yeah, I'll open it later. I'm just going to copy and paste this into my little notes over here. We'll use Zotero later. Do you need separate forward and backwards pass functions? Couldn't you just have one reaching function that moves the chain in one direction towards the effector, reverse chain, and then move it back? They're very, very, very close. The difference is where we find the bone length. So all of this code is the same, except in the forward pass, we set one direction, we reverse, which I don't think is really the issue. We could do, you know, we could build the iterator and pass it in. This is the difference. So in this case, the current position is the previous minus the direction times the current bone length. And in the other one, it is previous minus the direction times the previous bone length. So I think this is the only thing that in my head I can't abstract out. Maybe I can if I think it through a little bit more. But they are very, 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 very close. You are correct. I would not trust an LLM to do anything, especially summarize data. I think that it's basically like asking an unreliable narrator to tell you what happened in a movie. You can enjoy the movie if there's an unreliable narrator, right? But you're not going to have a factually accurate depiction of what happened. So no. I've seen too many examples of people who have given it some document that they wrote, right? Say, hey, I wrote this, like summarize it and compare like a rewrite, like give me a column of what I wrote and like what you would rewrite it as. And it can't do that. It can't even reproduce the thing you gave it. So no, I don't trust them. Not at all. Not even close. If I'm dealing with facts, I am not dealing with LLMs. Thus, in order to avoid cases, I don't think I don't think we have a fix for this right now, Xavier. I think that this is the case where theoretically there's a figure here, right? Figure 1A. This is figure 1A. This is the case where this is like a comparison. This is like an intra-chain comparison, right? So we've got this long bone and we've got the rest of the chain, which could happen at any point in the chain, right? This could happen later. If, I guess, does it need to be the root? That's another question. Again, I don't think we need to do this per se, because we do just hit max iterations and bail out. But it is interesting. I would like to this is one of those things where like I'm looking at it, I think it's interesting. It could result in some piece of code that could be useful. But we also like we don't need it for our current implementation to work. So yeah. The curl maintainer used to say something like the T in LLM stands for truth. Yeah. That's the other thing. Like LLMs have almost ubiquitously just made my life worse, so I'm not inclined to use them. Only at a glance, then you do independent research. I would not touch an LLM for anything that I don't understand. If you're looking for facts and you're looking for things that you don't understand to be explained to you, then an LLM is possibly one of the worst approaches you can use, because it will just lie to you and you will not know. And you won't be able to figure it out because you don't know. The fix is not basically not only use tolerance to end the loop, but also a max number of iterations. You think the fix is max number of iterations? I don't think fix, well, fix in some cases is max iterations. I think fixing in this case, I guess you would still want to do it. Like max iterations solves this, but it would still be cool to cut it out on loop 2 instead of loop 10. I don't think we need to, but we theoretically could if we wanted to do the extra calculation. Right, because this is a sub problem. of the whole bone chain. Right. This is a radius around the second joint, trying to reach back to that distance that is close to the root. So it's really saying, like, once we've solved the first, can we even make it back to the other one? Or I guess we don't even need to solve the first, right? But yeah, I think iterations works, but I don't know that it's the only way to terminate that, and we might be able to terminate earlier. And then they go on to say, like, in other cases, in the extreme case, the iterations are relied upon. So yeah. Yeah, today you asked the LLM a few questions regarding functions available for a library, and GPT-5 invented non-existing functions to solve your problems. Yeah, exactly. I would not trust an LLM to do anything relating to facts. If you're looking for like a summary, it is a bad tool to use because you do not know if that summary is actually what is said in the document. Or you could just read it. I mean, like, if you're going to read papers and you're going to read symbols, it's worth spending some time to learn the symbols, right? And then you'll know. And then you won't need to rely on the LLM. And like, saving time at the cost of being wrong is not a good trade-off, right? If you do it fast, but it doesn't work, like, that's not a good trade-off. What do I mean by LLMs made my life worse? The way that AI is currently being used, in general, makes my life worse. The way that summaries work on Google, for example, it's always the top results, right, above all the other results. And given the things that we just talked about, you can't rely on that summary to be accurate, right? And that's even if it gives you the sources, because you can go to the sources, and the sources could also be either AI generated or just fabricated in general, and the model won't know that. So when I look for something, I'm looking for a primary source, right? I'm looking for the GitHub document or the source code or the paper that somebody published, or like the first account reporting, or, you know, like, I'm looking for things that actually exist. I'm looking for that first party source for the material. I want the quote from, you know, the markdown file. I don't want a summarized, fabricated version of it, right? That's really not useful to the work that I do every day. The other thing is that, in general, the way that these LLMs and AI are being used are for things like my current apartment implemented one, right? So they use an AI chatbot to respond to me when I report issues. And that AI chatbot doesn't support things like attachments. So I can't send photos of issues in my apartment building to the apartment building managers because they have an AI chatbot in between me and them, right? Like, LLMs in general are making my life worse on a daily basis. On top of the fact that they don't do what they're advertised to do. It also, like, the number of people that come in with questions that are like, oh, I asked, you know, ChatGPT or whatever, and it gave me this answer. It's just not like, even just like regular stuff, right? Like, I was watching my friend play Pokemon Go the other day on stream, or not Go, sorry. They were playing ZA. And I was asking a question about the alpha Pokemon in ZA. and I asked it, and nobody knew because the game was so new. And somebody asked an LLM, and it gave them an answer, and they said it to me as if they knew. And then later said, oh, I had asked ChatGPT or whatever. And ChatGPT doesn't know because the game's been out for 12 hours, you know, like that kind of thing. It like routinely makes my life worse. There's also LLM generated responses in YouTube. See if I might be able to show this to you actually. Let me bring it up in my studio. Hopefully without doxing myself. I think this works. So look at this. Every video that I post now has these AI generated comments here, right? So now every time I go into studio, I have to avoid clicking these random AI generated comments so that like when I reply to you on YouTube, it's me replying to you. I don't click these things. I don't use a chatbot, right? But like this is the thing giving some feedback for like something they'd find better in a video. And it's just like so generic. It's like, glad you found it helpful and thanks for the feedback. I'll keep that in mind for future videos. And like, just click everything that says that. And then what are you doing? Are you even responding to people? Like, is this even a conversation if I click this button? Anyway, some of them are really bad too. That one was fairly reasonable as far as like a response would go, but like I have to avoid clicking AI shit all over the place. I have to avoid AI results all over the place. Everywhere that implements like LLM stuff just doesn't work correctly. It doesn't give me the thing that I'm looking for. Like it universally is making my life like worse. And it also doesn't work. Anyway, back to IK because I don't want to spend more time on this. Targets located on the kinematic chain. In the rare case where a kinematic chain is straight and the target is located on the line segments between the points, the algorithm is not able to find a solution. Really? I don't think I've run into that yet. I guess in the case of... Interesting. I would have to verify this with our current implementation. I don't know if this is true. I know that the bones tend to orient themselves in a straight line, but I'm pretty sure that if we have our 2D implementation, that is not true for us currently, right? Like this solve works for us. So there's something else about that comment that they're saying, right? This is solved for us. I guess if there is a joint restriction, right? If you can't bend this more than 45 degrees, let's say, then you can never reach this. That would be true. Which would be, I guess, what the paper is trying to talk about. That sounds real. The way the solver works would not converge in this exact case. Let's see. Kinematic chain. Okay, so the kinematic chain has to first be straight, which if I move the mouse, no longer becomes straight. And the target is located on the line segment between the points PI and PI prime. PI prime is the reflection of PI in the root joint P1. Okay, so it's some segment is the opposite end of the root node in a straight line all the way on the other side, which is just like a condition that we never see. Yeah. If you go out of reach and move the target in reach, but exactly in the same direction of the chain, it would not converge. Move the target in reach. I think you have to be in reach on the opposite side. Yeah. So here's the route. They're saying down here. They're saying past. Yeah, they're saying on the opposite side though. Well, I guess. Hang on. Let me. Why is P prime the between the points Pi and Pi prime? Ah, so between like P3 and P3 prime, there's a target, is what they're saying, I guess. So if there's a point, if the line is already straight, which we don't have the capability of doing in our current example, and the target is made to be on the current line, in this case, it wouldn't work because this can never actually reach that point anyway. Because theoretically, the way that it would work would be it would keep everything straight through this point, and then P4 would fail, effectively, is my understanding. Yeah. The way you see that the solver actually works, the opposite side would actually be okay. Yeah, I think you're right. Because then it would have to invert. I could see this though, because the way the algorithm would keep these two straight, and then the final one would be unable to actually touch the target due to the bone length. Assuming they were all exactly in the same place. So that makes sense. Unconstrained fabric converges to any given chain's goal positions when the target is within the reachable bounds, and there is a solution available, which is just a cool thing. It would set the tip to the target position, fix the bone length, which moves the root. Yes, which would then move the root back in the next phase. Yes, that makes sense. Infinite loop without any changes. Assuming it was exactly on that line, yeah. The algorithm is able to find a solution for any family of joints with a single chain of at least 3. See, I think the interesting thing here is that the algorithm treats all of these points, right? Like we were talking earlier about the end effector and whether the end effector should have a bone length on it or not. And this algorithm for all of the visualizations has a bone on the end that doesn't have a length. Which is why we have that end bone or the end transform in any case, because the paper has it. You have a question regarding learning in general. When do you need to learn a particular topic, do you use breadth first or depth first search? It depends on the topic. I think breadth first, in the sense of, if you don't know anything about a topic and you want to know more about a topic, then consuming a lot of media in various forms about that topic will give you, or start to give you, a vocabulary or the ability to recognize a vocabulary. And then you can start diving into specific things as you find them interesting and do isolated deeper dives on particular topics. I think in general, that's the approach that I take. So if it were going to be graphics 8 years ago and I didn't really know anything about graphics, it would be like start watching videos or reading blog posts or reading reading source code or anything, like anything that can give me kind of like a the nomenclature, right? Like anything that can start introducing me to the idea that a shader exists, the idea that vertex and fragment shaders exist, the idea that a compute shader exists, the name UV and what that means. Like anything that can give me more vocabulary is where I start. In certain cases where like I wanted to do inverse kinematics here, right? Somebody suggested FABRIK. I went, okay, cool, FABRIK. Let's do FABRIK. We went through the paper and the slides. We did the implementation, and now we're here going through another paper. So would you consider this a deep dive? Maybe. I don't know what you consider a deep dive. In my brain, I want to say it's not a deep dive because I know there are 4 other algorithms, you know, CCD, whatever, and et cetera. So having not done all of those, I feel like it's not a deep dive, but maybe that's breadth and depth at the same time. But yeah, I don't know. It depends. I think in general, if I'm approaching a new topic, gaining the vocabulary first, and then diving into specific areas is how I do it. I think I would have to have somebody else observe for me to really know. You know, I don't know that I can really give you, because I can give you like what I think is happening. But is it what is actually happening? I think I need a third-party observer for that. Do you feel a comprehensive or academic class is necessary as a form of FOMO for you? I don't think a comprehensive or academic class is necessary, no. I think in 2025, there is so much more information available than in 2000 on the internet that, like, for example, we can go read the FABRIK paper because it's just sitting on the author's website, right? And now we have a FABRIK implementation. So like, if you can find a class on inverse kinematics and it covers the things that you want, maybe, but like finding that class is going to be difficult. And then getting in to be able to take it is also going to be difficult. And not in like the content is difficult kind of way, but like the entrance to figuring out where those things are and how to get to them and how to do them are all difficult, if they even exist, right? Like, I don't know if there is an inverse kinematics class, right? There's physics classes. You could go do robotics and stuff. I don't know. Let's assume that MIT has one. Is the class reference for Drake. Here's FABRIK from lecture notes for robotics class, right? But do you want to do robotics, or do you just want to know about, you know, forward kinematics and inverse kinematics? Because you don't need to know all about robotics. And the use case for inverse kinematics for games and robotics is slightly different. Correction, the opposite side would not work okay. Same issue as the not opposite side. Interesting. More or less, the solver would not converge with the pose after fixing the root position would not be the same as the start pose. Interesting. Okay. Yeah, the mirrored pose. I could see it not converging, but just like kind of flipping back and forth in a line. Have you thought about how complicated it would be to expand FABRIK to arbitrary acyclic graphs of bones? What do you mean by arbitrary acyclic graphs? You mean like multiple end effectors and stuff? Or do you mean... I think as long as you have a tree, it might not be that hard. Unfortunately, the FABRIK papers aren't loading currently. Maybe I have it locally. Maybe I can bring it up. I do have it locally. Hang on. This is Zotero. So end effectors, subbases, root, FABRIK with multiple end effectors. This is about a couple of paragraphs. So let's just see what they have to say about it. Speaking of learning, this is kind of like the thing, right? Somebody asks a question. I don't know the answer to this question, but I know where to find the answer, or potentially find the answer instead. So FABRIK with multiple end effectors. This is the graph that I think you're thinking of, right? The previous topic is the FABRIK algorithm. So this is FABRIK with multiple end effectors. Hands, human-legged bodies, feet, etc. are comprised of several kinematic chains. Each chain has more than one end effector, so like a hand. Therefore, it's essential for an IK solver to be able to solve problems with multiple end effectors and targets. The proposed algorithm can be easily extended to process models with multiple end effectors. However, prior knowledge of the model, such as the subbase joints and the number and structure of chains, is needed. So you have to know something about the model, it's saying. Yeah, I think you've understood the question. Imagine you were doing a human and you wanted to set up IK-driven animations. Yeah. I think right now what I would do is I would just model each leg individually, right? One of the difficulties you encountered with FABRIK was multiple chains or tree branches. Even with one target, you'd have to make the chain consistent and drag the rest of the branches. What do you mean by that? Multiple chains or tree branches? Oh, you mean like if you have a loop in the chain? I don't know that this solves for loops in the chain. All the visualizations I've seen are trees. So I don't know that this actually has a solution for loops. And I guess theoretically, if you did have a loop, it would just be a solve for the shorter side anyway. Not a loop, but like one chain with multiple chains extending from it. Yeah, so a tree. So like this with the end effectors. That's what we're looking at right now. The multiple end effectors. So subbase joints. Subbases are anywhere where it splits. And the number and structure of chains. I don't know what kind of structure we need about the chains, but maybe that is just the discovery we do with this end effector component. So the algorithm is then divided into two stages, as in the single end effector case. So basically the same. In the first stage, the normal algorithm is applied, but this time starting from each end effector and moving inwards towards the parent subbase. So we do FABRIK on all the end effectors to each of the subbases. So if we had these, for example, each of these would go up to the subbase. So the root for the purpose of that FABRIK implementation or FABRIK execution would be this subbase on the left and this subbase on the right for all of these chains down here. This will produce as many different positions of the subbase as the number of end effectors connected with that specific subbase. The new position of the subbase is then the centroid of all those positions. So theoretically, you end up with a bunch of positions, and I guess you could average them together. Would that work? No, I don't know that that's the centroid. But calculate the centroid of that like theoretical polygon, right? I guess it's not a polygon, but you know what I mean. It's a bunch of vectors. Thereafter, the normal algorithm should be applied inwards, starting from the subbase to the manipulator root. Applied inwards, starting from the subbase to the manipulator root. Okay. If there are more intermediate subbases, the same technique should be used. In the second stage, okay, so apply algorithm, which I think is a forward-backward pass without a diff. Maybe with a diff. Forward-backward pass, end up with subbases in some positions. It's not clear to me whether they mean just run the back or just run the forward pass. Is the built-in PDF viewer in macOS? There is a built-in PDF viewer in macOS. This is Zotero. Zotero is where I put a bunch of my research. So for inverse kinematics, for example, Wow, it really doesn't let me collapse that, does it? I have these two things, which are FABRIK and FABRIK with model constraints. And then I can just click into them and read them. And I think I can actually like highlight things in here and stuff, although I don't do very much of that. So this just happens to be dark mode inside of Zotero. And then Zotero lets me export as bibtex, which I can turn into Hayagriva or use in my typist documents, which is part of the reason that I use typist now. Okay. I think the algorithm is divided into two stages as in the single end effector case. So I think we're only doing the forward at this point. So we do forward from end effector to subbases. This gives us a number of positions for the subbase, which we pick the centroid of, and then go back up to the next subbase, and then back up to the root, all with forward passes, doing the same thing. Yada, yada, more, where was I? In the second stage, the normal algorithm is applied starting now from the root and moving outwards to the subbase. Then the algorithm should be applied separately for each chain until the end effector is reached. More subbases, more iterations. Method is repeated until all end effectors reach the targets, or is there no significant change? So the diff is across all of the end effector positions. And there's some other stuff here too. So it seems like it would be pretty easy, quote unquote, to do. I think we would take the forward pass and the backward pass. We would need to know where the subbases are. We might be able to calculate that ahead of time. So if we go from the end effector and we do the whole chain for all of them, we could probably find commonalities between them, or we could just label them to start with. Hey, Pasta, how's it going? Yes, it sounds like the algorithm treats the tree like a set of subgraphs between each of the forks. That sounds right to me. Basically, every individual chain up to a subbase, and every chain like from subbase to subbase in the same way. Those are all individual applications of a forward or a backward pass. So for these end effectors on the right, there's two of them, right? We would do a forward pass up to this subbase for the left one, forward base up to the subbase for the right one. That gives us 2 points for the subbase. We pick the center point between them, which for two vectors will be pretty easy. And then we do a forward pass up to this subbase, assuming that this one did the same thing. This gets a centroid pick, and then we get this to root, which is just the root, so no centroid, it just is that. And then we go back the other direction. So we do the backwards pass from root to subbase, and then 2 backwards passes individually to the new subbases, and then so on and so forth. So we're kind of like doing tip to root, root to tip, and we're treating every intermediary collection of nodes as its own thing. So that doesn't seem difficult, actually. Eating pasta is how it's going. No pun intended. Yeah, I guess the question for me for these the multiple end effectors is it worth implementing that in the current examples, or I think that it can be built as another example, a different example. I don't necessarily have a use case, I think, for multiple end effectors is my only concern here. Like my end use case is spider legs, so I'm more interested in the constraints right now. But we can definitely get back to the end effectors, multiple end effectors, right? Because it does not look difficult, just a little bit more complex than the trivial solution because of the optimization in the mathematics of the solver. Yeah, I think that actually we already have all the code to do this. It's just that the iteration changes, right? So we need slightly different information. We already have the forward and backward pass, so it's just do the forward pass for all the chains up to the point, do the forward pass again for the next one, do the forward pass again for the root, and then from that point, do the backward pass from the root, do the backward pass down, and so forth. My question, I think, is, I guess the only thing that I can't think of off the top of my head is how do you get the resulting position for the subbase? Because if you, let's theoretically, you went to the last subbase in this example, right? That gets 2 points, one from each of the other subbases in the forward pass. You pick the centroid between those 2 points, and then you do another pass to the root. That pulls the root off, most likely, of the root, right? So then you put the root back on. You use the bone length from the root, and I guess the direction. Yeah, okay, so that just works in the other direction. Yeah. You still think there's an easier trivial solution that would work and handle multiple interfering IK chains with a lot more iterations? Maybe. I don't think the way they present in the paper is terrible. I think it seems fine from an implementation perspective. We have to prepare a little bit more data, I think, right? If we wanted to do it generically, we would have to discover all of the subbases, which I think we could do, right? If we do a bone chain, right, for every end effector. So every end effector goes up the chain all the way to the root, and we have that list of entities for everything. Then what we can do is find the entities that are common between different effectors and potentially do it like that. We could also literally just build the graph, and then we have queries like, is this have multiple children or not? Right? Like we could have a second data structure that is just the graph, which could be cool. We could do a pet graph. We could do basically all of the entities in pet graph and use that as an index structure, and then run the algorithm up pet graph. The iteration won't be expensive because we're going, very simply through a tree. We could also just store this like in our own way and iterate through it, but I think we end up with another index is what we end up with. I think it's just a little bit more data than I want to just toss around randomly. So having a tree structure that held entities and children, I think would be enough. Technically speaking, we have that. Right? Technically speaking, we have the child of relationship. Now, the question is whether the child of relationship is a bone or not, right? So basically we could go up from all the end effectors, turn that into one giant list of entities. Here are all the bones, right? And then iterate over children for any children that are in that list, going down one way. And then going up the other way, if we reach a parent that has multiple children in a list, then that is a subbase. Chris is live streaming. What a lucky day. Hey, Luke, how are you? Sorry if this was covered already, but what's the reason behind the work? How does this compare to the existing Bevy mod inverse kinematics and Bevy FABRIK? Thanks. This was just a learning experiment for me, personally. Bevy mod inverse kinematics looked like it also used FABRIK. Bevy FABRIK, I'm even less familiar with. Right, so I could have reached for one of these. How do I frame this? I don't want to sound like I'm reinventing the wheel here, right? Because like my intention wasn't really to ship a crate when I started this, but it also never is. My intention is never like, I'm going to build a crate to do, you know, Blender integration or whatever. It just grows into a point at which it's useful for other people. I think the thing that I find interesting about this whole process is, one, I wanted to know more about inverse kinematics. So read the paper, do an implementation, really get that understanding for what it is, translation it to 3D, really get that understanding, add maybe some model constraints, maybe more of the paper implementation. That stuff is all interesting to me. And then if I do that, that turns into really good content, right? So I will write posts about FABRIK and inverse kinematics and how it works. And I will make a video on inverse kinematics and FABRIK and how it works with visuals. And hopefully, having done this work, I will be able to produce something that can get somebody else up to speed a lot faster on inverse kinematics in general, and FABRIK specifically. If a crate comes out of this, which it might at this point, then it will be, you know, something. I don't know. Really, the goal that I'm trying to solve at the end of the day is tunic style spiders. Obviously, there are people who really enjoy the spiders. God, I really wish that I could get this happening without viewing actual spiders. Maybe they have a GIF in here. This thing right here. All these on the bottom left. These use IK for the walking. And I think, I don't know this for sure, but I think it's a 2-bone IK. So I think there's 3 joints. And I think there is not much in the way of constraints, but the joint has to point upward, you know? And there's something that we haven't gotten to, which is picking multiple targets along the ground as the spider is walking, that I really want to get to. But in general, yeah, the purpose of doing this originally was as a learning exercise for me. You use the setting that turns all spiders in Satisfactory into cats. Nice. Yeah, I know that some people feel weird about seeing spiders, and I feel bad about like surprising people with spider pictures. 200 IQ, 200 IK is a way to say where the tip of the chain should be Was there a question that I missed? Looks like Xavier's answering it, which is cool. If you do decide to extend the implementation by having a tree of bones, you could add the abdomen and body segments to get secondary movement. Is that useful? That could be cool. Yeah, so basically like a subnode that is the body. I think that the issue that I think of there is that the root of the legs and the body are static in relation to each other. So if you were going to use more IK to do that, then how do you attach the root of the spider leg to the body in a way that doesn't move? And that answer is, I think, constraints in this second paper that we were talking about. I think could be cool is maybe not sufficiently motivating for the added complexity. I don't know how much complexity it is. We haven't gotten through the other paper yet. We took a brief look at the, is Bevy FABRIK updated? No, Bevy FABRIK is also 2 versions out of date. So like, that's the other thing. I think Bevy Mod Inverse Kinematics is up to date and is kept fairly up to date by Kerbal. But I've never used it either. Yeah, see, like it's been up to date for a number of Bevy versions, which is great. So my goal here wasn't to like produce the ultimate Bevy IK FABRIK crate. My goal here was definitely just to learn some stuff. 200 IQ is how much IQ? I'm trying to learn bare metal programming on a Raspberry Pi. Get a display to work and render things on it. Yeah, it's a lot. That's a lot. Was that your first embedded project? That's a lot. That's yeah, I don't know. And Embassy only recently hit 1.0 and stabilized and stuff. Yeah. Too bad Tunic's crabs don't use this IK the same way they'd move. It'd be even more fitting for Bevy. We could make them crabs. We can do crabs. The thing in my head is if we do legs on a body, either for spiders or crabs or dogs or whatever it is, we have to have these other constraints. Which I think I have open somewhere. Yeah, so we haven't gotten through this paper yet, but this is extending FABRIK with model constraints, and it gets into that kind of like, how do you constrain things in a way that makes sense? We haven't really gotten to the angles and stuff yet. There's also constraints for multiple end effectors, it looks like. So yeah, there's some examples here of multiple different kinds of joints, like shoulders and stuff like that. I think we have to make it through this joint, these constraints, to be able to fully realize a spider that is fully IK'd and not just IK'd for the legs. Constraints is likely higher on the priority list than multiple end effector support. Yes, I think so. But if we're going to try to do that with the spider, then we will get to multiple end effector support. I think that will be multiple end effectors seems like it's a logical extension of what we have here, right? So right now, in the Bevy example repo, we have a 2D and a 3D. I don't know that these need to be really separate, actually. These can almost be the same crate, but we can have like another crate that is FABRIK multiple end effectors, right? And then I don't know if we have another one that's like model constraints and stuff or what. We'll figure it out. Your project is learning how all the IoT and computers work around us on a fundamental level. So your project is making a HAL for the Pico. Nice. That's so cool. And learning programming is part of the journey. You don't know how to program and you're making a HAL for the Pico? That's wild, yo. That's huge. That's a massive first project. Your learning process is very gruesome, but this is how I mean, if you enjoy it, that's really all that matters, right? I think that there's not many people who would say building a HAL should be your first project, but if that's what you really enjoy and you're finding it great, then sick. That's all you need. For all the things I say about like pedagogy and education and stuff, it all comes back to really just one thing. And it's if you want to keep doing it tomorrow, then it's the right thing to do. Right? It doesn't matter if you know the basics. It doesn't know if you know the core essentials or whatever people think those are. It doesn't matter if you learn a framework. It doesn't matter if you do, you know, a game or embedded or web or, you know, kernels or networking or CLI tool or whatever. As long as you want to do it again tomorrow, that's really all that matters. Because if you can do it again tomorrow and you do it again the next day, then eventually it'll be 5 years down the line, 10 years down the line, and you'll be like an expert. As long as you keep doing it. If the IK chains share bones, the branching subbases issue Chris is investigating, then solving these two IK in the same thread and even the same solver loop is required. Yeah. Anatomically accurate starfish for the IK chains. Is this the Krusty Krab? Cool. So we'll probably get to multiple end effectors. It sounds like we actually, I think making the spiders like fully IK could be interesting. And then maybe we could use some of these constraints for like keeping the body a certain level above ground and stuff like that. I think that could be very interesting. This is all, at the end of the day, this is all for the scheme demo. So, I mean, this is a huge detour for the scheme demo. You want to get into Bevy again, though? Got to get some variation. Totally agree. Just go on because you enjoy it. Yeah, I mean, if you're having fun and you want to do it again tomorrow, that's really at the end of the day all that matters. Everything else is like just somebody else's opinion, yo. You know. Okay, so we haven't gotten through this paper yet. This is going to be a bit of a paper investigation stream, I guess, is what this is turning into. Reachable, non-reachable targets. Okay, so we made it to proof of convergence. I think these aren't necessarily super useful. It's important to note that if the kinematic chain is not straight and the target is within bounds, then the kinematic chain will never be in a straight line after a full set of iterations. So we never need to worry about it deadlocking itself, which is cool. Iteration ends when forward and backward has been completed. By construction of the algorithm, forward and backward are identical in process, which they are. Thus, we look at the iteration as two repetitions of one forward step and one backward step. Do we have a heading for what we're getting into? Proof of convergence. Okay. I don't think we need to care about proving this converges. People who say it cannot be done should not interrupt those who are doing it. Yeah, absolutely. I think these are just visualizations of the propagation. Maybe that's useful to get into. But we don't really need to prove that this works. We have an implementation and it works. Forward and backward reaching inverse kinematic. What font is that? I don't know. My ADHD kicks in. What font do we think that is? This section aims to show the flexibility of the algorithm and how it can be adapted to a wide variety of problems. We extend the multiple end effector version of FABRIK to identify whether a target is reachable, offering optimization solutions that return the final posture in just one iteration. We also adjust FABRIK to cope with closed loop problems with chains in which the end effectors are not positioned at the end of the chain. Oh, there's your answer for loops. And for interjoint distance control. The solutions presented can be extended or modified. So maybe we do need to go back and do multiple end effectors before we do this paper, because it looks like they're building on top of multiple end effectors. Solutions can be presented, can be extended or modified to solve different models in a similar manner. Note that the cases described in this section are constraint-free, but they can be easily adjusted to consider joint limitations as described in section 5. So section 5 is really what we want to be able to get to in reading this paper. Multiple end effectors. One of the benefits or main advantages is multiple end effectors. Most models, many kinematic chains. And I do learn new things as well. And my measurement of success is by talking about things on Discord with OS devs and getting understood what I'm talking about. Nice. That's awesome. Yeah. One of the reasons that I really enjoy hanging out in the Bevy space is that there's a lot of people in a lot of different disciplines that know a lot more than I do. So kind of just giving back from the information that I've gotten on these streams and videos and stuff. As described in 1, algorithm is divided into 2 stages. The first stage is forward pass all the way back up to the root. They basically just re-describe the multiple end effector description that we covered in the last paper using these paragraphs. Huang and Pellichat, let's see if I can, we're on page 40. What paper is this? Huang and Pellichat, an efficient. So there's another paper here, an efficient energy transverse inverse kinematic solution. We're not going to look at it. This is not for this stream, but just to call out that there is a reference here to something else. Multiple end effectors. Okay, reachable and non-reachable targets. They recently presented an alternative of the FABRIK multi-end effector solution using an energy transfer approach. The sub-base position has the same use and properties, however, is directly obtained from the mass spring model. Flexibility of FABRIK allows a variety of different solutions based on, that's cool. So they add a little bit of mass spring to the positions of just the sub-bases. So this could actually be, let me add this to Zotero, added. That's how easy it is for me to add things in there. You wonder if this multiple end effectors can be used to do things like poles in Blender. Yeah, I haven't seen any mention of poles yet. I'm assuming it can because they do talk about humanoids, and I don't know if you all know this, but knees are only meant to bend in one direction. I know, shocking. Elbows, same way, actually, only meant to bend in one direction. So if we're talking about humanoid armatures, then I believe that this will be handled. As in the single end effector case, highly advisable to check whether targets are even reachable or not. In the multiple end effector models, there are more instances to consider. So for simplicity reasons, they describe a 2 end effector case. But theoretically, if there were a bunch of them, we could end up with more potential cases. Oh, so that's why it hurts when I try to do it in the y-axis. In this section, for simplicity reasons, okay, first step is to check whether targets are within the reaching area. Hence, the distance between each target and the root should not exceed the sum of the interjoint lengths. So this is the same check that we did in our FABRIK implementation. Just to show that on screen. Right, this circle here is how far these bones can reach for this distance. So if we have multiple end effectors, they each have their own circle, which is the same calculation. Knees bend in many boy bands, not just One Direction. You got me. You got me. That's what I was thinking of when I said One Direction too, actually. Some people can bend their elbows in both directions. Yeah, I mean, the axis, or rather the the angle past 180 degrees is not very much. Okay, there are 3 different instances in the case where both targets are outside, one target is out and another is in, and both are in. So we're just talking about 2 end effectors here in the multiple end effector. So it's becoming increasingly obvious that we have to do the multiple end effector solution to be able to apply this paper. Because it sounds like whatever they're going to do in the context of multiple end effectors. So maybe we could simplify it and apply it to a single end effector. But they're sure mentioning multiple a lot. So FABRIK applied in its usual, so if they're both out, right? 3 instances. The first case is both are outside the reaching area, in which case we hit the max iterations, and we get a straight line starting from the root joint. However, optimized version can be applied. I think this is just 2 end effectors from the same root. I think this is not using subbases. This is just describing like a V. However, an optimized version can be applied. During the forward state of the algorithm, move the end effector to the target position. Thereafter, the new intermediate joints are repositioned to lie on the line that passes through the end effector and the subbase. Oh, there's a subbase here. Keeping approximate interjoint distance fixed. This process will return 2 straight kinematic chains and 2 new possible positions for the subbase. New subbase position is assigned to be their centroid. Then normal applied to joint root. On the backward step, move the root joint to its initial position and apply FABRIK till the new subbase. Thereafter, the remaining joints are positioned on the line that passes through the new subbase position and their corresponding target. Okay. So the way that we get that angle from like the end effector or like any joint to a position, this is saying that we go from the subbase to the target and line up all of the joints on that target. And we have already lined them all up in a line by doing the forward pass. So when we go backward and we hit that subbase, then we get to skip, I think, the rest of the calculation. And this is, I think, the visualization of that. So there's 2 targets. We've got a Y shape, not a V shape. There's a subbase involved here. So forward pass moves both of these to 2 different points, and there's a centroid. And then we do the centroid for both of those positions. Question being, I think that's just a move. And then we do down to the base. And then going back out, pulls this down, which I guess ends up putting it in a good position. And we finish out to these edges and we end up with straight lines. That makes sense to me. Makes sense to y'all? Can optimize or not, up to the user. Cool. We'll skip optimizations until later. In the last case, both targets are within reach. Nevertheless, there are 2 possible cases. The case where both targets are reachable, in which case the normal multiple end effector version can be applied, and the case where it is only possible to reach 1 target. Yep, even if both targets are in the reach area, nothing assures us that they are reachable. That makes sense. If no optimization procedure is applied, neither end effector will reach the target, but both will be the same distance from their corresponding targets. Interesting. Explaining the algorithm in text, clear as somewhat translucent mud. If you have questions, feel free to ask them. Happy to go over this stuff. Explaining the algorithm in text and images and not pseudocode does not make sense, but okay. Yeah, I don't know. It's a paper, you know? I think the visualization would help some people, for sure. Okay, targets on the chain. I think we can skip that. Closed loops is another thing that we talked about, where end effectors can be in the middle of a loop. This is figure 5. Where's figure 5? This is figure 5. So this is the closed loop visualization. Theoretically, if we have a triangle, right? So this is also like, if we're going to build a crate out of this, then we can build these up as demos, examples, right? So if there's a triangle where P1 is the end effector, chosen end effector, then that goes to the target, right? Move to direct to target. We go counterclockwise in this case around to put that into a straight line. We straight line the next one along the vector. So this is the same calculation that we've always been doing. Then it seems like there is the calculation back to the original and the re-expansion of the other vector. So there's an extra vector calculation here to put that triangle in the right spot. So we don't really need to know how that works right now. We can just say that, yes, that works. See, where are we? 11 o'clock? Okay. Joint control and serial chains, true 2 joint positions. Joint control and closed loop chains. So there's a whole bunch of like extra information about different cases and whatnot and how things work, which is very cool. So it seems like end effectors no longer need to be the end of the chain, which is really interesting. So we can move P4 here to that target and then move everything towards P4. You like images? I think images are good. Absolutely. I think the more variations of media that something can be explained in, the better. Because different people land on different things. Okay. Self collision determination. Okay. Incorporating joint and model restrictions. This is really what we wanted to get to. Human models, as most legged body models, are comprised of joints having motion restrictions, like we talked about earlier. Thus, in order to keep movements within range and reduce any visually unrealistic movements, model constraints. Essential in physical simulations and motion tracking. In one, it is shown that FABRIK supports rotational and orient. Where's one? Oh, in the last paper. In the original paper, it's shown that this is possible, is what they're saying. You like when the images move and you can step forward and backward in time? Nice. Maybe we'll build some interactive visualizations of the model. That's another thing. We can do all of this extra. So there's so much that we can do, right? We can do the implementations for 2D, 3D, extend it to multiple end effectors, extend that with model constraints, and so on and so forth. We can do that in a blog post write-up. We can share the code as well. We can make a video on it with visualizations. We can also build a like a demo, right, that we can deploy on itch or something like that, that lets you just place a couple of yes, and typist that lets you place a couple of bone positions and then like a target and iterate through the steps, which would also be very cool. It's just that all of this takes time is really all it is. I like the idea of showing the algorithm in action, I think. So maybe we do build a little demo site for all of this when we're done with it. You're saying we a lot for someone who's doing all the work so far. I mean, y'all are in chat. We're discussing this. Like, bugs have been caught by chat before. You know, it's we. I think while we're on stream, it's we. You know, even if I'm driving the car. It's a bit like pair programming, right, or mob programming in that sense, where yes, I'm driving where we're going to, but that doesn't mean other people aren't involved. In this section, we extend the rotational and orientational usage of FABRIK. Okay. A joint is defined by its position, orientation, and in the most general case has 3 degrees of freedom. Degrees of freedom? DOFs? Backseat programmers. Hey, there's a name for it. The essential feature of a joint is that it permits a relative motion between 2 limbs it connects. Bone rotation can be factored into 2 components. One simple rotation, named rotational, which is 2 degrees of freedom, that moves the bone to its final direction vector, and another called orientational, which is 1 degree of freedom, which represents the twist around this final vector, which totally makes sense to me. That is like, how do you get it from here to point at the thing? And then once it's pointing at the thing, like where is your thumb pointing once you rotate? Thus, the range of movement of a bone can be controlled by dividing the joint restriction procedure into 2 interconnected phases, rotational and orientational. That's cool, because the orientational is kind of what we're taking care of right now in our current algorithm. Contributing equally to the joint restriction. The operating mode of the algorithm for incorporating constraints is the reposition and reorientation of the target to be within allowable bounds. Because FABRIK is iterative, joint restrictions are enforced at each step of the algorithm to ensure that the target is within limits, and if it is not, to guarantee that it will be moved accordingly. Another paper mentioned here, that is an alternative implementation of FABRIK that is based on the intersection of circles. So this is another paper. This is also what you get into. Once you start reading papers, they're like, oh, and we talked about this one, and we talked about that one, and we referenced this one, and there's this other one. What is up with papers being able to be downloaded today? There's like, there we go. Okay, throw this into Zotero before. It says MS Word Guidelines for SBM4. That's the wrong title. Cool. So let's get back up to what we were just looking at. What figure is this? 8? This is a reference again to the other paper that we looked at earlier, or that we decided to not read earlier, I should say. So they use a geometric approach to control rotation and orientation of a robot, while the rotational and orientational limits are controlled independently. Wang and Pelchod describe how to incorporate joint restrictions and energy transfer. That's the other paper. They check all joints rotation values after the mass spring process, and if the rotation in local space is out of bounds, they modify the model to exclude these values. When you started, how did you deal with the nervousness or fear of failure in front of everyone on stream? I mean, you're gonna fail. That's just gonna happen. You just gotta like, you gotta get used to the idea that not everything you do is perfect the first time. And I think the more you realize that that's the case for everybody, and the more you see your failures actually helping other people, the easier it is to acknowledge that, right? Because there are things where I fail at them on stream, and people are like, "Oh, but the process you used to deal with that was really useful for me." So like even in failure, dealing with failure is a thing that is useful. Also, the only way to get through things, the only way to get to like a good thing is to fail a bunch first, right? That's just like, nobody can do it perfect the first time. That's not possible. So you just got to get used to the idea that like, you got to learn how to build stuff up. You got to learn how to approach problems, break them down into simpler problems, hopefully succeed at simpler problems, and then move up to more complex ones. Which is kind of what we're doing here, right? Like, I didn't know about FABRIK. I read FABRIK on stream. We got through it. It had bugs. I know Xavier was feeling particularly antsy about some of the bugs it had. We fixed the bugs over time. It's now stream number 3. We are looking into like constraints and stuff. Just like your HAL a huge mistake. I wouldn't call your project a huge mistake. Like so I actually feel very strongly about this, even when people are joking. Don't self-describe as kind of like shitty. Don't like, there's no reason for you to tell somebody else to not like your stuff, right? Literally no reason, right? Not only because you actually don't know how much value somebody can get out of the stuff that you produce, but also like priming everybody to not like what you did is just a bad habit to be in. It's a really bad habit. Yeah, and a learning experiment is not a mistake anyway, right? It's hard to fail at streaming. You can fail to solve the problem, but that's not the same as failing to be entertaining or informative. Absolutely. Yeah. Yeah. I don't think, like, there's a bunch of people who know more about FABRIK who have been in chat. Right? People come in and they're like, oh, I implemented FABRIK and had XYZ problems or whatever, right? That's really funny, Xavier. So there's a bunch of people who know more about FABRIK who have been in chat. There's people who know more about Rust than me who have been in chat. There's people who know more about Bevy than me who have been in chat, especially different subsections of Bevy, right? I think if there's a place where I still have nerves, it's definitely in the whenever I see a name come up in chat that I recognize and respect their work, I'm like, oh shit, I hope that I'm doing an okay job. But you just have to deal with that at some point, you know, like that just like, that's not a reason to not do something, right? And as long as you're not like, as long as you're not sitting here trashing stuff and not, you know, shitting on people's work for no reason and whatnot, like you're free to make as many mistakes as you need to get to the point where you understand what's going on. And especially people who know things, people who really actually know things do not judge you for not knowing things, right? Like people who really actually know things are interested in the fact that you are also interested in a thing, right? If you ask questions, or like put the effort in and visibly put the effort in, people who have the answers really appreciate that and are more likely to give you answers in response. Okay, so joint restriction models presented in this paper should be considered an illustration of how joint or model constraints can be incorporated within FABRIK. Similar techniques can be easily adopted to limit different joint models. So anthropomorphic joints. So figure 10, which is not figure 8, shows the 6 joints discussed in the paper. Ball and socket, hinge, pivot, condyloid, saddle, and gliding, indicating where they can be found on a human body. What is a condyloid joint? An oval-like surface that is received into an elliptical cavity. It's like your hip. Two is a condyloid. Okay. Okay, interesting. So they differentiate between ball and socket and condyloid is all it is. Where condyloid is more oval, and ball and socket is literally a sphere. This is a bad habit of mine. I just isolate and learn in my little corner, but every time someone sees your stuff, they're usually impressed rather than, oh, your drawing has bad proportions. Yes, absolutely. You don't even need a medical student for that. You need somebody who did like some athletics in the past or in some physical like physical education stuff. You don't even need medical students for that to learn about joints. Yeah, I mean, like that's one of the reasons that like publishing stuff is really useful, right? You're building your own how, but like there's a bunch of people that don't even know how to build their own how. So if you had a blog or you just posted things in gists or whatever, and we're like, hey, here's the progress that I made today. Hey, here's the progress that I made today. Then somebody else who's searching for it can actually find it. And given that you've already done it and they haven't, you know something that they don't. You don't need to know everything. You just need to give an explanation of how you did it. Okay, so try to get through a little bit more of section 5. Start looking at some of these joints. And then I think that'll be it. Very true, yeah. Okay, so Ball and socket and hinge were originally presented in the original paper. In this paper, we demonstrate how joint restriction can be incorporated into the most common anthropomorphic and robotic joint models. More sophisticated models, such as shoulder, can be formed by combining these techniques. Ball and socket are spheroidal joints. Rotary movement in every direction within certain limits. Most mobile type of joint in the human body. On the other hand, the hinge joint is the simplest type of joint. It can be found in the elbows, knees, and the joints of the fingers and toes. So we need an elbow joint, I guess, or a hinge joint for our spiders. And maybe a ball and socket for the legs of the spider. Your wrist and your hip can move in the same kind of way, but there's something your hip can do that your wrist can't. Let's twist your leg around its long axis. Yeah. But the wrist is like a bunch of bones, right? Like I guess I don't really think of my wrist as a joint. I think of my wrist as like a collection, a complex collection, right? Right? Like a wrist is not a joint. In game development, it could be, but in anatomy, I think the wrist is quite a few things, and not a singular thing. We could talk about the radial carpal joint individually, maybe. But like, there's so many bones in your wrist. Yeah. Wrist is that complicated word. Okay. You think the ball and hinge joint can be done? Oh, did they ask something that I missed? Or did you try to tag me and tag the wrong person? Yeah, wrong at. Okay. You think the ball and joint and hinge joint can be done by the same implementation, just maximum rotation for each axis? Yeah. Yeah. Yeah, wrist is super complicated. Yeah. You realize you forgot all basic anatomy from school? Good thing it's a Google search away then. So ball and socket, hinge. We're talking about hinge only permitting motion in one plane or direction about a single axis, flexion and extension. Procedure for orientational and rotational control for ball and socket and hinge is described in detail in the first paper. Really? We'll have to read that section. A ball joint can also spin as well as hinge in all directions. Yeah. I mean, technically, yes. Just imagining my leg spinning. It's not making me feel great about my leg. Pivot joint is one in which a bone rotates around another, permitting only only rotating movements. It can be found in the neck, allowing a side-to-side turn of the head. Candyloid joint. Biaxial movement, forward, backward, and side to side, but not rotation. This is figure 9. I feel like the images are, the text is way outpacing the images because we were just talking about figure 10. Here's figure 10. Ball and socket in the hip, condyloid in the, we're saying condyloid is the wrist. Plane joint in the ankle. Saddle joint also in the wrist. Hinge joint in the elbow, pivot joint in the neck. You need to disconnect all your ligaments and stuff in your leg to actually do that, of course. Yes. Yes, that's exactly where my head was going. The condyloid joint seems a bit more complex. The maximum rotation around an axis is dependent on the rotation on the other axis. Okay. Gliding, saddle joint, robotic joints. Prismatic joint is a 1 degree of freedom kinematic pair, mainly used in robotics and mechanisms. Prismatic joints provide a single axis sliding function with the axis of the joint coincident with the center line of the sliding link. Yada yada. This family of joints changes the size of the links connecting the joints, and thus it is generally not supported by most IK solvers. That's prismatic joints. However, FABRIK can be adjusted to deal with prismatic joints if details about the permissive variations of link sizes are available, or if the maximum and minimum sizes for each link are a priori known. Cool. So theoretically, we can turn one joint into some kind of a gap, which I think Xavier was bringing up at one point, where having like disconnected bones is an interesting case. And I think that is saying that this prismatic joint is related to that in some way. Gliding joint. Self-body dynamics. The main assumption of the IK problem is that the interjoint distances remain constant over time. However, especially in human models, bones allow a small fluctuation in length size that most researchers in the literature use a mass spring model to describe. That makes sense. Therefore, there is a need to allow IK solvers to increase and decrease the interjoint distance. That's really interesting, because that means that theoretically, for any given joint, we could need two transforms. Two transforms that try to be in the same place, but don't necessarily make it to the same place. Prismatic joint is the proper name for what you called pneumatic arms earlier. Okay, yeah. Okay, dealing with a deadlock. We haven't even gotten there yet, so let's skip that. Human geometry. Bunch of ball and sockets and stuff. End effectors on fingers. Like chin and cheekbones, and then toes. Hierarchical structure of a human would be shoulders out to fingers, and then a closed loop around the torso. This is just like one way to do this, I'm assuming. And then a closed loop with two thigh bones, and then each of the legs from the hip down. So there's a little bit of overlap here. Okay, let's see. As the end effectors start to move around, FABRIK relocates the hand chains and the upper triangle to meet the interjoint distance assumption. So there's some little like expansion that can happen in the shoulders. That feels weird. This process moves the subbase to its new position. The algorithm is iterative and will be repeated till the distance works. Second stage of the algorithm, FABRIK is applied to reposition the 3 remaining chains. First, it is applied to control the lower triangle of the main body, then the legs. How do you pick these positions? Subnodes? I guess if you reach a subnode that has a closed loop, you kind of have to process that closed loop on its own. So there might be some setup work for more complicated IK chains, especially with these model constraints. In this model, it's assumed that the feet should remain constant. So the feet should always be rooted, which I guess makes sense, right? Because you're usually walking on something. FABRIK is incorporated to reposition the head chain. This is not an iterative process because it's treated as a serial chain. Yeah, because there's no chain here. It's just... this apparently was integrated into mocap software. That's cool. And then experimental results. So it feels like there's not that much about actually implementing this in the paper. There's not that much talk about the joints and what you actually need to do to them. So it might be a little bit experimental for us. I think we'll start with a hinge joint maybe in the next stream. Well, we will start with multiple end effectors. We have to do multiple end effectors first. Once we do multiple end effectors, then we can start doing joints. I'm not really seeing much description of like how to implement the joints at all. The pivot joint, initial configuration, the forward, backward, target is projected and whatever. Robotic joints, anthropomorphic joints. Maybe I missed it. Maybe I said it earlier and I just skipped over it because I was talking about something else. Rotational and orientational. The joint restrictions are enforced at each step of the algorithm. So the question is are the joint restrictions enforced for each bone or for each joint as we iterate over it or after the pass? You found a paper covering all of this with pseudocode text and images. Cool. What's the paper called? What's the name of it? It sounds like the original paper has joint limits. I think it'd be worth double checking that implementation for details. Yes, absolutely. Was noticing that they kept calling back to the original paper, and I don't think I gave the original paper enough of a read over for those restrictions. I kind of jumped to end effectors. So joint limits. So really the next paper is about those closed loop chains then, right? Right, a joint is defined by its position and orientation, 3 depths of field, 3 degrees of freedom. See, this is just like a repeat of, well, this isn't the repeat. This is the original. Assume we have a ball and socket joint with orientational limits described by the rotor R, and rotational limits described by angles 1 through 4. Graphical representation of a joint limit boundary could be an irregular cone, which is defined by these angles. Rotational limits are enforced by repositioning the target point as the nearest point on a conic section from the target position. This procedure is described in detail later. So that's this ball and socket. Right, so we've got P1 and P2, and this bone can move in, I guess there is no other, where's the other bone? There's only 2 bones in this demo. Guess it doesn't matter. So that rotates and then basically has to project onto the cone. So we kind of have to track the rotation as we're going through the whole thing. Interesting. Yeah, the papers you were just talking about, but you didn't say what the titles of the papers were, did you? Or did you post them in Discord or something? Oh, that is the original paper. That is the original paper, as far as I'm aware. Right, that's the one we're looking at currently. Right. This is the person. These are the papers. This is the paper that you were just talking about. This paper is the paper we're looking at currently. Whereas the model constraints paper is the one we were reading before. So we are on, I don't know, page whatever of the paper here. Didn't show up in the chat. Yeah, I don't, the whatever link like thing that you posted didn't show up. So I don't really know. Didn't see that. But the paper that you posted in Discord is the original FABRIK paper, and that's the one that we have here. Okay. Assuming we're in the first stage of the algorithm, we've just calculated a new position of point or joint Pi prime. We want to find the new position of the joint I minus 1. I minus 1. Find the rotor expressing the rotation between the orientation frames at joints Pi and Pi minus 1. And if this rotor represents a rotation, so we need to actually care about the rotation during the algorithm now. Whereas before we didn't. Right? So we're going to start working with transforms, I think. Pseudocode and algorithm 2, figure 4. Is this figure 4 right here? This is figure 5. Figure 4 is, I think, this one on the right. So we've got pi plus 1, pi, and then the rotational rotor S theta 1, 3, 4, 2. So they're defining this rotor by 4 angles for each of the quadrants. And then the constrained joint into the constraint has to pick a point for the joint. If theoretically it was off to the side, it would pick a point on the edge of this position. And this happens when is the question I have in my mind. The last question I want to answer. Right, the orientational constraints. The rotor R expressing the rotation between the orientation frames. So we do need the rotations here, I guess, or we need to calculate the rotations, I guess. Anything? I think we need to calculate the rotations. The new reoriented joint, check whether the rotor is within the, if within bounds, then do nothing. If it's not within bounds, reorient. So just snap it to the place. And then we go over the rotational constraints, which are slightly different. Okay, so there is more here, but when is this happening? You didn't realize the original paper went this far. You'd only seen some simple chain demonstrations on YouTube. Yeah, because the simple chain demonstration is like the easy part, I guess you might say, or the like. When people refer to FABRIK as being a simple algorithm, the forward and backward pass that we looked at earlier, like these two things, like while diff, forward pass, backward pass, this is so simple in that sense compared to thinking about rotors. I would, I don't know. I don't have an opinion on using rotors in the paper, but it definitely feels like they could have used something else. It's giving draw the rest of the owl. Kind of. I think I missed a place where this is supposed to be taking place. That's the thing that I'm looking for in the paper right now. This talks about joint definitions. A reliable methodology for incorporating constraints. So it says the joint restrictions can be enforced at each step by taking the resultant orientation and forcing it to stay in the valid range. So the question in my mind is at each step after a forward pass, or is at each step after a bonus processed? When is this happening is the $1 million question that the paper doesn't explain. You can't find it either. But it is somewhere inside the solver loop. You would do it every time a node position is changed in the solver loop. I think that, given what I know about the algorithm, the intuitive place that I have in my mind to place this is do the forward pass, do the constraint, then do the backward pass. Don't change the forward pass at all. Just do the constraint between forward and backward. Because if we do it in between forward and backward, in my mind, the way this works is we move the end effector into the target spot and yank the chain, right? Have a good night, Sorov. We move the end effector into the target slot and yank the chain. which pulls the root off, right? And then we do any constraints that we need to do, right? Which moves things around again. And then the backward pass replaces the root back into the right spot and yanks the chain in the other direction. And I think because this is iterative, if we do everything in that orientation, then we get to do forward pass, corrections, backward pass, forward pass, corrections, backward pass. And I think that will work. But I will give a little bit of a deeper reading to this to figure out if I've missed something or not. In the meantime, I'm feeling pretty hungry, so I'm going to stop there, and we'll get back into this probably. I don't know if the next stream is going to be Bevy. The next stream might be Rust language workshop scripting. So that might be Thursday morning. And then that would give us probably Friday and Saturday for more Bevy stuff. We'll see. But that's going to be it for today, and I will catch you all in the next one. Have a great rest of your day, y'all.